What if a star just vanished? Not exploded. Not collapsed into a black hole. Not swallowed by some monstrous galactic event. Just faded away. As if someone slowly turned down the dimmer switch of the cosmos until it blinked out of sight. No drama. No finale. No explosion lighting up the sky. Just gone, quietly. For years, astronomers have catalogued stars with a sense of certainty. Once it's mapped, it's there. A fixed pin in the vast tapestry of night. But what if even that can't be trusted? What if there are stars that behave like cosmic ghosts, appearing, disappearing, flickering just at the edge of human perception? One of those stars is V529 Orionis. But before we continue, subscribe to the channel. Tucked in one of the most recognizable constellations in the sky, Orion, this mysterious object does something few other stars dare. It sometimes fades into nothingness. Not metaphorically. Literally. Telescopes pointed at its coordinates have, at times, seen nothing. Just black. As if the star had never been there. And then, sometimes it returns. A flicker. A faint point of light. A whisper from the dark. V529 Orionis doesn't behave like most stars. It doesn't pulse with regular rhythm like a Cepheid. It doesn't brighten and dim predictably like an eclipsing binary. It doesn't even burn out in a cataclysmic nova. Instead, its vanishing act is slow, silent, and terrifyingly uncertain. What could make a star disappear like that? This question haunts the few astronomers and amateur observers who still follow its strange light curve. And for good reason. If we can understand stars like V529 Orionis, we might discover that the universe is hiding more than we think. In a sky full of fixed points and known constellations, V529 reminds us that nothing is ever as permanent or as understood as it seems. Not even the stars. Perhaps that's why it's so easy to overlook. After all, how do you study something that sometimes isn't there? The story of V529 Orionis is not just a tale of astronomy. It's a cosmic ghost story, a lesson in humility, and a reminder that the heavens still hold secrets. To find V529 Orionis, one must first look to one of the most beloved patterns in the night sky, Orion the Hunter. This constellation has inspired stories for millennia, from the myths of ancient Greece to the celestial lore of cultures across the globe. Orion's belt, formed by 3 bright stars in a nearly straight line, is one of the easiest asterisms to identify. Hanging from that belt is Orion's sword, an area that appears less distinct, softer, almost fuzzy to the naked eye. It's within that sword that the story of V529 begins. Nestled among the stars of the sword, close to the dazzling and more famous Orion Nebula, M42, is where V529 Orionis resides. M42 is bright, bold, and full of star-forming activity. It is one of the brightest diffused nebulae in the sky, visible even without a telescope under dark skies. Naturally, it draws most of the attention. Rightly so, its brilliant glow and swirling clouds of gas are nothing short of awe-inspiring. But that's exactly why V529 Orionis often escapes notice. It lurks in this crowded, chaotic stellar nursery, one of the busiest intersections in our galactic neighborhood. Observers, both professional and amateur, are so drawn to M42's vibrant detail that they rarely pay attention to its dim surroundings. And yet, just a faint step away, V529 flickers like a cosmic trickster. When it's visible, it can be spotted with a small telescope or good binoculars. When it isn't, well, it's simply not there at all. Not detectable. Not measurable. As if the universe had erased it temporarily. The star lies very near the Trapezium cluster, a group of hot, young stars that power the glow of the Orion Nebula. Amid these powerful stellar lights, V529 is like a candle in a stadium. You have to know exactly where to look. Even with modern equipment, it requires careful calibration and patience to separate its faint light from the visual noise around it. And yet, despite being located in such a high-profile part of the sky, it remains strangely anonymous. Part of that anonymity is due to its intermittent nature. It's not a steady resident of this patch of sky. It comes and goes, sometimes over weeks, sometimes over years. This erratic behavior makes it a moving target for stargazers. A star that doesn't always show up is a star that doesn't always get logged. In fact, many star catalogs simply omitted it when it disappeared during survey windows, as if the star had never existed. But to the careful observer, especially one tracking the Orion region over many nights or seasons, V529 Orionis stands out precisely because of how elusive it is. Stars generally don't just vanish, especially not in one of the most studied and photographed areas of the entire night sky. So its disappearance isn't just inconvenient, it's profoundly unsettling. There's a poetic irony in this, too. Orion's sword is traditionally thought to be the hunter's weapon, a symbol of power and visibility. And yet within that very sword lies an object that defies visibility itself. It flickers, hides, returns when least expected. Like a celestial sleight of hand, V529 Orionis undermines the very notion of stellar permanence. A ghost among giants. This makes its location all the more baffling and brilliant. Among the young, hot stars of the Orion Nebula, and in the glare of M42, sits a star that seems almost to protest its own existence. It hides not in the depths of a forgotten sky, but in the very heart of a cosmic spotlight. It's as if the universe placed one of its strangest objects in plain sight, but gave it a built-in cloak of invisibility. Even professional observatories can miss it during its dimmest phases. This has led to no small amount of confusion over the years, especially when old sky charts are compared to new ones. Sometimes it's there. Sometimes it isn't. But its coordinates, its position in Orion's sword, those remain the same. It's a cosmic paradox. Fixed in place, yet not always present. To understand V529 Orionis, one must learn not just to look, but to look again. Because the first glance may not reveal the truth. That's the nature of a disappearing star hiding in one of the brightest and best-known regions of the entire sky. Perhaps the most haunting thing about V529 Orionis is its flickering. Not the soft, steady dimming that defines many variable stars. No, this is something stranger, more ghost-like. The star doesn't just grow fainter. It can vanish completely, slipping beneath the threshold of human and even digital detection. One night it's there, barely, a whisper of light on a CCD sensor. A few nights later, nothing. This isn't just theoretical or anecdotal. Multiple observations, separated by years and even decades, have recorded the same phenomenon. The star fades so dramatically that even sensitive instruments can no longer detect it. Not just a reduction in magnitude, an erasure. Astronomers have used terms like invisible, absent, and non-existent in their logs. It behaves as though it wants to be forgotten. It's this extreme fading, often abrupt and without a clear periodic cycle, that earned V529 Orionis its reputation as a flickering ghost. Most variable stars pulse in predictable rhythms. Some, like mirror variables, wax and wane over long cycles. Others, like Cepheids, beat like the hearts of the galaxy, their periods tied to their brightness. But V529 doesn't dance to any known rhythm. It doesn't pulsate. It disappears. This erratic behavior raises countless questions. Is the fading gradual or sudden? Sometimes it seems to dim slowly over weeks. Other times, it practically drops off the map within days. When it reappears, it often does so without warning, as if someone flipped a cosmic switch. But why? What could cause such deep, irregular fading? And more disturbingly, how many other stars might behave this way, escaping our notice just because we're not watching at the right time? Some early observers doubted their own eyes. Reports from the mid-20th century described the star fading past the 17th magnitude, far below naked eye detection, and difficult even for modest telescopes. Later, it would return to around 13th or 14th magnitude, still faint, but visible again. And then it would fade once more. These wild swings in brightness have no obvious external trigger. No nearby object seems to be blocking it. There's no nebula dense enough to account for the full range of dimming. It's as though the star itself controls its own visibility. What's even more confounding is how little attention this star has received despite such bizarre behavior. In part, this is because it never gets particularly bright. Even at its maximum, V529 Orionis is far from eye-catching. Most amateur telescopes have to work just to detect it. That means it's been easy to miss, or dismiss, or overlook. It's a ghost in every sense, faint, forgotten, and flickering at the edge of perception. But its brightness, or lack thereof, is not the only thing strange. The light curve of V529 is chaotic. It doesn't follow the sine wave smoothness of a pulsating variable. It doesn't repeat like a binary eclipse. Instead, the curve looks erratic. Sometimes jagged. Sometimes flat. Sometimes it plunges into darkness and stays there for a while, refusing to return. If the star were a heartbeat, doctors would call it arrhythmic and prepare for resuscitation. But this is no dying star in the traditional sense. It's something else. One of the unsettling things about this star is how confidently the universe seems to hide it. It isn't loud. It isn't explosive. It simply disappears. It draws no attention. And yet its vanishing act may be one of the purest mysteries of modern observational astronomy. It behaves like a phantom caught between two realities, sometimes existing in ours, and sometimes slipping through some unseen crack into silence. For the few who have tracked it, the experience is strange. One night you align your telescope, scan the area, and there it is, faint, flickering, real. You blink. Real again. Then, a week later you look again, and it's just not there. Same coordinates. Same time. Same settings. Nothing. There's something poetic, and also a little chilling, about a star that can vanish so completely. Not explode. Not be absorbed. Just choose, in some cosmic language, not to be seen. As if some celestial instinct tells it when to shine and when to hide. To call V529 Orionis a variable star is technically accurate, but practically misleading, because it behaves unlike almost any other variable star ever catalogued. The term, variable star, encompasses a wide range of stellar types whose brightness changes over time, but most of them follow well-studied and reasonably well-understood rules. Cepheid variables, for example, expand and contract in size due to internal pulsations, and their brightness rises and falls in a precise rhythm. These stars are so reliable that they're used to measure distances across galaxies. RCRB stars do the same, albeit on shorter timescales. Eclipsing binaries, another common type, vary in brightness not because of internal changes, but due to an orbiting companion periodically passing in front of them, dimming their light from our perspective. Even more chaotic-seeming variables, like flare stars or cataclysmic variables, tend to reveal patterns when observed over long periods. V529 Orionis breaks those molds entirely. It doesn't pulse with regularity. It doesn't display an identifiable period. Its dimming is not caused by an obvious eclipsing partner. Its outbursts, or rather, its vanishings, don't correspond to any predictable trigger. The usual light curves that define types and behaviors of variable stars turn into unhelpful noise when applied to V529. In many ways, it acts more like a cosmic glitch than a coherent astronomical object. Most variable stars show some consistency. You might not know when they'll flare, but you can guess the range in which their brightness will fluctuate. There's a sense of control in that chaos, parameters that obey the physics of stellar atmospheres, thermonuclear fusion, dust clouds, and orbital mechanics. But V529 Orionis doesn't obey. At times, it has stayed faint for years, as though hiding behind an opaque veil. Other times, it returns quickly, teasing observers before vanishing again. There's no clean on-off switch here. No algorithm can currently model its behavior with any certainty. This sets it apart in a field already full of oddities. Consider for a moment how the science of variable stars has advanced. We've catalogued tens of thousands across the sky. Modern surveys like OGLI and OSIS-SN have automated the monitoring of these stars, generating light curves across months and years with incredible precision. Through these efforts, astronomers have been able to group variables into well-defined categories based on cause, period, amplitude, and spectral type. But V529 Orionis remains stubbornly unclassified. Even among the rarest known types, it stands out. Some researchers have loosely associated it with the enigmatic Aurora borealis, RCRB, stars, which are known to undergo sudden and deep drops in brightness due to the formation of carbon dust clouds in their atmospheres. These clouds block the star's light temporarily, causing it to disappear until the dust dissipates. But even RCRB stars eventually return to their baseline with some regularity. V529 Orionis is less cooperative. Its fades are deeper. Its reappearances, more tentative. Its timeline, less structured. The mystery goes deeper than observational oddities. It challenges our theoretical understanding of how stars evolve and behave. A star doesn't just lose light without a cause. Some mechanism, be it intrinsic, within the star, or extrinsic, outside the star, must account for the fading. And yet, years of intermittent study have yielded few concrete answers. The data is fragmented, scattered across decades and different observers, because its dimmest states often correspond with long periods of neglect. And this is part of the problem. Stars like V529 get missed because they defy the expectations baked into modern survey techniques. Automated sky surveys are brilliant at detecting recurring behavior. Algorithms are trained to recognize and flag familiar variable patterns, periodic dips, bursts, flares. But when a star behaves like V529, it sometimes evades detection altogether. If it vanishes during a survey's run, it may simply not be logged as a candidate for variability. And if it's too faint for a telescope's limiting magnitude, it doesn't even get recorded. So we're left with this peculiar star that doesn't seem to care about our desire for order. It doesn't play by the rules. It's not just unusual, it's anomalous. And anomalies are where science often makes its most exciting discoveries. V529 Orionis may represent more than a single weird star. It could be part of a class of objects we've barely begun to understand. Its erratic light curve, deep vanishing acts, and lack of a spectral or temporal pattern suggests that we may need to invent a new subcategory of variables just to contain it. Or perhaps we need to admit that not all stellar behavior fits within our existing frameworks, that some stars are, for now, beyond classification. In this way, V529 serves as a kind of boundary marker, one of the farthest edges of what we currently know about stellar variability. Just as the discovery of quasars shattered preconceptions about point sources of light in the sky, or how pulsars forced us to rewrite the life cycle of stars, so too could V529 hint at some deeper, undiscovered process at work in stellar evolution. It's even possible that it reflects some rare stage of stellar transition, an identity crisis, so to speak. Stars don't evolve in clean, discrete steps. They age, they shift, they shed layers, they pulsate, and sometimes they do strange things we weren't expecting. V529 may be in a transitional phase that is poorly represented in the current population of known stars. And if that's the case, it's not just an oddity, it's a valuable key to a hidden chapter of stellar life. This is why continued observation is so vital. V529 Orionis cannot be understood through occasional glances. It requires persistence, patience, and long-term photometric monitoring. It requires coordinated global efforts from amateur astronomers, robotic observatories, and deep sky surveys that don't skip over objects just because they're missing one day. It also requires humility. Because a star like V529 reminds us of something essential in astronomy. The sky is vast, and our knowledge, though growing, is still fragmentary. We have named and studied countless stars, but some still slip through our fingers, not because they are too far away or too faint, but because they refuse to conform. V529 Orionis is, in the purest sense, a flickering ghost. A star that breaks the mold. A beacon of mystery in a constellation filled with clarity. And though we struggle to define it, perhaps that's the point. Some celestial objects exist not to be solved, but to keep us searching. The earliest intrigue surrounding V529 Orionis begins not with a grand discovery, but with a series of quiet observations, ones that, at first glance, seemed unremarkable. It was the early to mid-20th century, a period when astronomy was rapidly evolving, bridging the gap between the naked eye and the machine-assisted observations that would define the modern era. Photographic plates were becoming standard tools for sky surveys, allowing astronomers to freeze the heavens in time and return to those frozen moments again and again, comparing one decade to another. These plates, monochrome, grainy, but remarkably precise, would become the first forensic evidence in the mystery of V529 Orionis. V529's earliest confirmed mention dates back to photographic surveys in the 1920s and 1930s. It was spotted near the Orion Nebula, but only faintly, just bright enough to make it onto plates taken with sensitive emulsions and long exposures. In those days, variable stars were a hot topic. With the success of Henrietta Swan Leavitt's work on Cepheids and Edwin Hubble's application of those variables to measure the distance to galaxies, the sky was under intense scrutiny for anything that flickered. V529 didn't stand out, at least not initially. It was just another faint star in a crowded patch of sky. But that changed. By the 1950s, when photographic surveys were repeated and earlier images re-examined, inconsistencies began to emerge. The star was visible on one plate from, say, 1932. On another plate from 1941, taken at the exact same coordinates with the same or better sensitivity, it was gone. Not dimmed. Not faded. Gone. This was no minor fluctuation. It was an absence. Astronomers didn't know what to make of it. Faint stars near bright nebulas can be tricky. Light pollution, atmospheric conditions, and even emulsion variability on photographic plates could all influence what got recorded and what didn't. So the initial instinct was caution. Perhaps it was an observational error. Perhaps the star was misidentified. Perhaps a flaw on the plate had mimicked a star that wasn't there. But the pattern continued. In some observations, V529 reappeared. In others, it remained absent. Not just dim, but undetectable even on plates that showed much fainter stars nearby. The star began to build a reputation, not for what it was, but for what it wasn't, reliably visible. Throughout the 1960s and into the 1970s, amateur astronomers began to take notice. This was a golden age for dedicated stargazers, individuals with personal observatories, access to increasingly powerful backyard telescopes, and the patience to track obscure targets night after night. Some of these observers began logging notes on the star. Reports came in that echoed the photographic record. One observer in 1966 saw it faintly and marked it near 14th magnitude. In 1969, another checked the same coordinates and found nothing, just black space where the star should have been. There were even occasions where V529 seemed to fade during the course of a single observing season. One particularly dedicated observer in the early 1980s noted that the star was faint but visible in early January, only to become undetectable by March. Whether this was due to the star dimming or the growing interference from Orion's setting position in the sky isn't known, but the possibility that V529 faded significantly in just a couple months added another layer of mystery. And then there was the issue of star catalogs. In some catalogs compiled from plate surveys in the 1950s and 60s, V529 was included as a faint star near M42. But in later revisions, particularly those based on surveys conducted during one of its off phases, the star was simply missing. It wasn't removed, it had vanished from the data. Modern observers comparing catalogs have noted that V529 appears inconsistently across databases. Some include it as a known variable. Others omit it entirely, either because it wasn't visible at the time of observation or because it fell below the limiting magnitude for the equipment used. This inconsistency in historical records is not common. Variable stars might change in brightness, but they rarely disappear so thoroughly that they fall off professional catalogs. And yet V529 did, multiple times. It's difficult to overstate how bizarre this is. Stars, at least those within our own galaxy, do not just disappear under normal circumstances. Even stars shrouded in thick clouds of gas and dust can usually be detected in other wavelengths, infrared, radio, or ultraviolet. Yet V529 seems to elude even that. Its absence from visible light records suggests not a dimming, but a temporary vanishing, a complete optical silence. One of the most tantalizing pieces of historical data comes from a comparative study done in the 1990s, where astronomers went back and digitized dozens of old photographic plates. Using modern image processing software, they could enhance, align, and contrast images that were once interpreted by eye. In doing so, they confirmed the vanishing acts of V529. Not only did it disappear in some decades, but in others it appeared unexpectedly bright, brighter than expected for such a supposedly faint star. This raised another possibility. Was V529 not only fading to invisibility, but occasionally brightening beyond its usual faintness? Was this a flickering star in the truest sense, not just dimming, but also occasionally surging? The data wasn't conclusive, but it was suggestive. Perhaps V529 wasn't just a fading star. Perhaps it was a truly erratic one, brightening, fading, and disappearing on a timeline only it understood. A ghost, yes, but a ghost that sometimes cried out. And through all this, one strange reality persisted. Nobody could agree on what kind of variable V529 actually was. Its vanishing behavior was unique. Its location near M42 complicated photometric readings due to background light from the nebula. And its lack of consistency made it a poor fit for almost every known variable classification. So it remained largely untouched, a curious footnote in observational astronomy, a whisper among the many voices of Orion. But those early historical sightings, scattered though they are, remain invaluable. They are breadcrumbs across time, hints that this star is not an illusion, not an artifact, not a glitch in our equipment. It is real. It is out there. And for a century or more, it has been playing its disappearing game, just beneath our notice. The most haunting signature of V529 Orionis is its ability to perform what can only be described as a disappearing act, episodes where the star vanishes entirely from the sky, becomes undetectable by even professional equipment, and then, sometimes unpredictably, returns as though nothing had happened. These episodes are more than mere fluctuations in brightness. They are complete absences. Erasures. One night, a whisper of light. The next, a void. This isn't poetic exaggeration. This is data. The disappearing act was first truly noticed when careful archival comparisons began to accumulate in the mid-20th century. Before that, the star's faintness meant it was often ignored or glossed over. But as more photographic plates were developed, digitized, and analyzed, a pattern of vanishing began to emerge, one not tied to a strict period or repeating cycle, but rather to erratic and perplexing episodes. These weren't subtle dips in magnitude. These were dramatic, absolute absences. Moments where the star fell below the threshold of detection entirely. Imagine a researcher in the 1970s, reviewing a plate from the 1940s and seeing a faint star near the Orion Nebula. Curious, they check a newer plate from a recent sky survey. They look at the same coordinates, same resolution, same exposure. Nothing. Black sky. Other stars nearby remain fixed in place, glowing as they always have, but V529 is gone. What's the explanation? A cataloging error? A misidentification? These were the theories at first. But the more it happened, the less likely coincidence became. Eventually, a consensus began to form among those who paid close attention to this strange region. V529 Orionis was performing a vanishing act. And not just once. Repeatedly. There are several documented cases now where V529 vanished entirely from observational data for extended periods of time. These aren't brief, single-night occurrences that could be attributed to perceived conditions, clouds, or instrumental failure. They're episodes spanning months, or even years, when the star simply did not appear. It was as if it had been plucked from the sky, its place marked only by memory and unanswered questions. And then it would come back. Without fanfare, without warning, it would reappear at its usual faint magnitude, around 13th, 14th, or 15th, depending on the phase. The reappearance was just as mysterious as the disappearance. There was no predictable lead-up. No gradual brightening. Just absence one day, and presence the next. Some of the most confounding examples of this come from long baseline studies where observers tracked the region season after season. In one case, amateur observers in the early 2000s noted the star missing for the better part of 2 observing seasons, nearly 18 months. They double-checked their charts. They recalibrated their scopes. They consulted other observers. Some had seen it previously, others hadn't. And then, suddenly, one clear night, it was back. Same spot. Same faint flicker. As if it had never left. This behavior deeply unsettles those accustomed to the constancy of the cosmos. Stars aren't supposed to just disappear. The night sky is supposed to be our most stable clock, our most immutable map. And yet V529 Orionis breaks that quiet agreement. It flickers in and out of existence with a kind of eerie autonomy. Even more mysterious is that the star's returns do not always match its previous brightness. Sometimes it comes back fainter than before. Sometimes brighter. But rarely, if ever, does it behave as if its fading and reappearing were part of a clean, sinusoidal cycle. Instead, its light curve resembles a scrambled heartbeat, with dips and rises in no clear order, and those long, flat lines where no light at all is detected. This raises a critical question: what could cause a star to do this? There are a few known celestial phenomena that can mimic disappearance. Our coronae borealis stars, for instance, are known to suddenly dim by several magnitudes when carbon soot clouds condense in their atmospheres and block the light. These stars are rare, and their behavior is unusual, but it's at least been studied. And yet even they don't vanish to this extreme. Most remain faintly visible. V529, on the other hand, can go completely dark. Another possibility is extreme eclipsing by a companion object, a binary system where the primary star is periodically obscured by a dense cloud, disk, or companion star. But again, these systems tend to be periodic. You can set a clock by them. Eclipses follow orbital mechanics. The timings are predictable. V529 follows no such logic. It disappears at seemingly random intervals, for unpredictable durations. The lack of periodicity may be the most puzzling part of all. If V529 had a consistent rhythm, say, a deep eclipse every few years, or a carbon cloud forming every decade, we could classify it. We could model it. But its pattern is chaos. A logic that, if it exists, is buried beneath layers of complexity we have yet to understand. There's also the consideration of external obscuration, not from the star itself, but from materials surrounding it. Could V529 be embedded in a rotating or shifting dust shell? Perhaps a cloud of matter left over from a previous evolutionary stage? Maybe even the early stages of a planetary nebula? These scenarios could account for irregular dimming, but they don't fully explain the stark disappearances and abrupt returns. Compounding the mystery is the fact that V529 resides in Orion's sword, a region dense with nebulosity, gas, and interstellar dust. Could foreground material be contributing to its vanishing act? Or is the obscuration intrinsic to the star's own environment, possibly the result of mass loss, a remnant disk, or failed stellar winds? These are all on the table, but none can definitively explain the specific behavior V529 exhibits. Even in the infrared, where dust is more transparent and cooler objects are easier to detect, the star has shown inconsistency. In some IR surveys, V529 emits a signature, faint, but present. In others, it's missing altogether. This suggests that whatever is causing the disappearing act might affect multiple wavelengths. Or, more intriguingly, that it's not just light being blocked, but perhaps even the light source itself fluctuating in power. Could we be witnessing a transitional stellar phase? A brief window in a star's evolution where internal processes cause catastrophic shifts in brightness? If so, then V529 is a rare glimpse into something fleeting and possibly unrepeatable. Perhaps we caught it in the act of dying, but not in any way we've seen before. And this is what makes the disappearing act so much more than a curiosity. It hints at something we don't understand. Something lurking in the blind spots of our theories. Something playing hide and seek with the rules of stellar physics. For now, We can only watch. Wait. Log the appearances and absences. Add one more point to the erratic graph. Because every reappearance is a reminder that the mystery isn't over. Every vanishing is an invitation to look deeper. When V529 Orionis first started attracting attention for its strange vanishing acts, the astronomical community was hesitant to accept the phenomenon at face value. After all, the idea that a star, especially one located in a region as well studied and luminous as Orion's sword, could completely vanish, only to reappear later, stretched credulity. The scientific method demands skepticism, and in the case of V529, that skepticism manifested as a wide array of alternative explanations, many of which sought to reduce the mystery to human or mechanical error. Could this really be a disappearing star, or was it all an illusion? The earliest hypotheses centered around the limitations of observational equipment. Photographic plates, though revolutionary in their time, were far from perfect. Chemical emulsions varied in sensitivity, development processes introduced inconsistencies, and minute variations in exposure times could affect what appeared on the final image. Furthermore, stars located in areas of high background luminosity, like the region around M42, were especially vulnerable to being drowned out. Light from the surrounding nebula could easily overwhelm faint stellar points, leading to situations where a star present in one image simply didn't appear in another due to marginally different imaging conditions. And so, for a time, V529's disappearances were attributed to such mundane causes. Perhaps the star wasn't gone. Perhaps it was just overwhelmed, drowned in the sea of Orion's light. Perhaps an inexperienced observer had mistaken a dust speck or a plate flaw for a real star in one image, and thus falsely claimed its disappearance in the next. Confirmation bias, coupled with the subjective nature of early astronomical analysis, may have amplified the illusion of variability. Then came the consideration of alignment errors. Because Orion's sword is dense with stars and nebulosity, precise alignment of observational equipment is crucial. Misalignment by even a fraction of a degree could cause an astronomer to miss a faint star entirely. In early observations done manually, such errors were not uncommon. A slight shift in pointing, or an incorrect coordinate transcription, could lead an observer to search the wrong spot and fail to find the star. This led some to suspect that V529 Orionis wasn't disappearing. It was simply being looked for in the wrong place. Other astronomers proposed that the star's identification itself had been flawed. Perhaps the original sighting was a case of mistaken identity. Maybe V529 had been confused with a nearby variable or faint foreground object that only resembled a star. After all, the catalogs of the time, though precise by the standards of the era, were prone to mislabeling, especially in crowded fields. Could it be that V529 never existed at all? That it was a ghost of paperwork, an illusion born of cataloging errors and human assumptions? For a while, these skeptical interpretations held sway. Scientific conservatism, especially in the realm of celestial objects, tends to resist dramatic claims unless they're backed by overwhelming, repeatable data. Extraordinary behavior demands extraordinary evidence, and V529 offered only ambiguous hints from scattered observers and aging photographic plates. Until more reliable data could be gathered, it would remain an astronomical footnote, a curiosity, not a crisis. But even as these skeptical theories gained traction, counter-evidence began to accumulate. Observers began coordinating their efforts. Charts were checked and double-checked. Observations were made with better equipment, under controlled conditions. And crucially, the same strange behavior continued to appear. More than one observer, using different tools and on different nights, would record the star's reappearance, only to see it fade again weeks or months later. The development of CCD imaging further sharpened the debate. Unlike photographic plates, CCDs provided quantitative brightness measurements with far greater sensitivity and consistency. With this new technology, astronomers were finally able to track stars like V529 in more detail. And once again, the story repeated, periods of visibility, followed by absence. Not a one-off error. Not a failure of equipment. A real, repeatable pattern. Skeptics then moved to new ground. If the star truly was disappearing, perhaps it was due to a foreground object, like a thick interstellar cloud, that passed between Earth and V529 on occasion, blocking its light. This was plausible. The Orion region is replete with complex clouds of gas and dust, some of which are only barely mapped. Perhaps V529 happened to sit behind a particularly variable cloud whose density or position changed over time. But this too faced problems. No other stars in the immediate area were reported to exhibit the same behavior, and deep sky images showed no dense dust features that could explain repeated, selective blocking of just one star. Another theory leaned on the idea of seeing conditions, atmospheric distortions that affect Earth-based telescopes. Maybe V529 was always present, but Earth's atmosphere blurred its light so much that it simply fell below detection thresholds at times. But this would also affect many other stars in the field, and it didn't explain why repeated observations under excellent seeing still occasionally showed no trace of the star. Eventually, the weight of repeated disappearances across different observers, instruments, and decades began to turn the tide. What had once been dismissed as observational error or illusion began to crystallize into something undeniable. The phenomenon was real. V529 Orionis was doing something strange, something that defied explanation, but could no longer be reduced to human error. Modern surveys, with their automated sky-scanning telescopes and precision photometry, have confirmed that V529 does indeed fluctuate in brightness in a way that is not merely extreme, but at times, total. These fluctuations have been observed even when equipment is functioning perfectly, even when the data is double-checked by multiple independent sources. It is now accepted by most in the variable star observing community that V529's disappearing acts are not an illusion. They are a legitimate astronomical phenomenon, rare and poorly understood, but real. This shift from skepticism to acceptance is a familiar one in astronomy. Time and again, strange objects have emerged from the noise, quasars, pulsars, fast radio bursts, and have faced initial resistance until further evidence forced a re-evaluation. V529 follows in this tradition. A star dismissed for decades as a glitch or mistake, now reclassified as a genuine anomaly worthy of study. And so the question changes. No longer, is this real? But, what could possibly make it real? If the star's vanishing is not the result of our flaws, our eyes, our tools, our theories, then it must be the result of something in the universe itself. Something hidden in the dark, playing tricks with light, leaving behind nothing but a blank spot in the sky, and a growing sense of cosmic unease. With all the skepticism that once surrounded V529 Orionis, claims of optical illusions, errors in old photographic plates, misidentification, or flaws in equipment, there eventually came a turning point. The moment when doubt gave way to data. And that moment was delivered by the rise of modern photometry. Modern photometry, the science of measuring the brightness of celestial objects with high precision, has transformed how we observe the universe. Instead of relying on subjective impressions or grainy photographic plates, astronomers today use charge-coupled devices, CCDs, sensitive detectors capable of counting photons with astonishing accuracy. These digital sensors, coupled with powerful image processing algorithms and telescope automation, have ushered in a new era of sky surveys and stellar monitoring. V529 Orionis, for a long time, was hidden in the gaps of earlier observational efforts. Too faint for the casual observer, too erratic for the catalogs that preferred orderly, cyclic stars. But as survey techniques became more sophisticated and the sky began to be mapped in high resolution, night after night, from all over the globe, V529 re-emerged, this time with numbers to prove it. One of the first major reassurances that V529 was not an illusion came from the digitization of old plate archives. Projects like DASH, Digital Access to a Sky Century at Harvard, began scanning over a century's worth of photographic plates and translating them into brightness data that could be plotted and analyzed. Across this vast temporal dataset, V529's flickering stood out. Not only did it disappear in some epochs, but its variability was consistent with an object that was truly fluctuating in brightness, not just being masked by local noise or background light. These historic observations, when matched with modern data, formed a coherent, if erratic, light curve, validating the earlier records and connecting the past to the present. But it was real-time photometry from robotic telescopes and wide-field survey missions that truly sealed the deal. Programs like OSIS-SN, All-Sky Automated Survey for Supernovae, and the Zwicky Transit Facility, CTF, began monitoring large portions of the sky every few nights, catching transient phenomena with precision. These surveys operate with automated pipelines that process data and flag interesting variations. And while V529 doesn't light up in supernova-level bursts or follow neat patterns, it started appearing in the raw photometric data as a confirmed variable, clearly changing in brightness across months and years. Importantly, these modern instruments operate with redundancies and calibration systems that make it extremely unlikely for a genuine object to disappear due to error. Each observation is cross-referenced with calibration stars, atmospheric conditions, and instrumental baselines. When V529 fades in this data, it is not because something went wrong. It is because the star genuinely faded. Photometric measurements in these surveys show V529 dipping below the detection threshold, around magnitude 17 or fainter, and then reappearing at brighter magnitudes, sometimes around 13. These are significant changes. A difference of 4 magnitudes corresponds to a decrease in brightness by a factor of about 40. In astronomical terms, this is not a mild variability. It's dramatic. Even more fascinating is how the fading and brightening don't correspond to a repeating cycle. When plotted on a graph, the star's light curve doesn't form a sine wave, or a repeating notch like an eclipsing binary. Instead, it looks like jagged terrain, sharp drops, long plateaus of invisibility, occasional rebounds. Sometimes it brightens gradually. Sometimes it seems to blink out rapidly. Sometimes it stays faint for months on end. It is this erratic behavior, captured with modern instruments, that has confirmed V529's status as a real and active variable star. In addition to optical photometry, infrared observations have also contributed to the case. Observations from infrared sky surveys, such as 2MASS, 2-micron all-sky survey, and WISE, Wide Field Infrared Survey Explorer, have at times detected faint excess emission at V529's coordinates, suggesting the possible presence of dust or cool circumstellar material. These data points reinforce the idea that something real, and not an artifact, is influencing the star's light output. And then there are the amateur astronomers, an unsung army of patient watchers who have used their own telescopes and CCD cameras to track V529 across months and years. Their data, often shared with organizations like the American Association of Variable Star Observers, AVSO, adds another layer of confirmation. These dedicated observers, working independently yet harmoniously with professional efforts, have helped build out the long-term light curve of V529, catching it in both its visible and invisible states. When professionals miss it due to survey windows or maintenance gaps, amateurs often fill in the blanks. Together, their records form a consensus that cannot be ignored. Today, databases like the AVSO's International Variable Star Index, VSX, include entries for V529 Orionis that reflect its true behavior. Its status is listed as variable, with notes on its irregular fading, location near M42, and history of disappearing from view. It's been cataloged, logged, and relogged enough times that its identity is no longer in doubt. Still, it's important to emphasize just how unusual this confirmation is. Most variable stars are identified and classified in days or weeks. Their periodicities are determined quickly, their types pinned down with a few nights of spectroscopy and photometry. But V529 has resisted this neat wrapping for decades. Its unpredictability, location near the glow of the Orion Nebula, and faintness have made it one of the most elusive variables to confirm. And yet here we are. After a century of observational noise, guesswork, and skepticism, V529 Orionis has earned its place among the confirmed mysteries of the sky. It is real. It is a star. It is variable. And it fades, not slightly, not subtly, but dramatically and completely, for reasons still not fully understood. Its very existence now forces us to reconsider how many more stars might be hiding in similar masks of invisibility. How many other variables flicker in and out of detectability, escaping the fixed gaze of our surveys just because they don't behave the way we expect? How many stars disappear not because they die, but because something stranger is happening? V529 has transitioned from doubt to confirmation, but its story is far from over. Now that it is known, we can watch it more closely. We can study its light, its infrared signature, its spectral lines, if any can be caught during a visible phase, and its neighborhood in space. We can add it to our lists, our maps, our databases. And in doing so, we can begin the next chapter, not just observing the mystery, but understanding it. Now that modern instruments have confirmed V529 Orionis is not just a real star, but an undeniably variable one, we arrive at the next and perhaps most frustrating question: what kind of variable star is it? This is where the story takes another mysterious turn, because, quite simply, V529 Orionis does not fit neatly into any known classification of variable stars. It slips through the fingers of categorization the same way it slips from the field of view during its long disappearances. It's not just that we don't know why it fades. It's that we don't even know how to label it properly. Let's begin by stepping back to understand the types of variable stars astronomers have grown familiar with. Variable stars are usually divided into two broad categories: intrinsic and extrinsic. Intrinsic variables are stars whose brightness changes due to physical changes within the star itself, like pulsations, eruptions, or internal instabilities. Extrinsic variables, on the other hand, change in brightness because of external factors, like being eclipsed by another star or obscured by surrounding dust. Each of these categories has many subtypes. For example, Cepheid and RR Lyrae variables pulsate with remarkable regularity due to cyclical expansions and contractions of their outer layers. Their variability is so predictable that they are used as cosmic yardsticks for measuring galactic distances. Then there are Mira variables, which are late-stage giant stars that pulsate slowly but dramatically, with brightness fluctuations over periods of hundreds of days. On the extrinsic side, we have eclipsing binaries, systems where two stars orbit each other and periodically block each other's light from our point of view. These create very regular light curves, with periodic dips every time one star moves in front of the other. There are also rotating variables, whose surface features like star spots or oblate shapes cause apparent changes in brightness as the star rotates. But none of these comfortably describe V529 Orionis. Its variability is not regular. Its periods of disappearance do not follow a set timeline. Its brightening and fading are not symmetrical. And its amplitude of variation, the range between its brightest and faintest state, is far larger than what we see in most standard variable types. So, let's try to match V529 Orionis with the closest known analogs, and watch how it evades everyone. One early candidate was that it might be a type of our Corona Borealis, RCRB star. These rare stars are famous for fading dramatically and unpredictably, sometimes by several magnitudes. Their fading is caused by sudden ejection of carbon-rich material, which condenses into dust clouds that temporarily block the star's light. This can make them disappear from view for months or even years. And at first glance, V529 fits this model. The deep, unpredictable dimming. The prolonged absences. The eventual return to brightness. But there are problems. RCRB stars are usually hydrogen deficient, carbon-rich supergiants in a very specific evolutionary phase. Their spectra show unique features. Sharp molecular bands of carbon compounds like C2 and CN. We have no spectral data of this kind for V529, because it's often too faint for spectroscopy during its dimmest phases, and during its brighter phases, it's not yet been studied in enough detail. Worse still, V529 is even more irregular than most RCRB stars. RCRBs eventually return to brightness over months or a year. V529 can remain vanished for years with no sign of recovery. Some of its disappearance episodes appear even deeper, borderline complete in terms of optical silence. That's not typical of RCRB behavior. So while the comparison is tempting, it doesn't fit snugly. What about a T Tauri star? These are young, pre-main sequence stars still in the process of forming, often embedded in dust clouds, and known for irregular brightness. They are usually found in star-forming regions, and Orion certainly qualifies. T Tauri stars can be erratic, and their light is often influenced by circumstellar disks and accreting material. But V529 doesn't appear to be a young star. It doesn't emit strong X-rays or show UV excess typical of T Tauri types. It doesn't sit in one of the densest young clusters. And again, the extent and nature of its fading don't match known T Tauri light curves. It's more extreme, more silent. Another suggestion has been that V529 could be a symbiotic variable, a binary system involving a red giant and a white dwarf, with mass transfer occurring between them. These systems can have unpredictable brightness due to changes in accretion rates or eruptions from the white dwarf. But symbiotic variables are often much brighter in infrared and show strong emission lines in their spectra. V529 does not display these indicators. Its spectrum, when visible, has been described as ordinary and lacking the complex signatures expected of mass transfer systems. Some have even proposed it might be a dusty Post-AGB, asymptotic giant branch star, an evolved object shedding its outer layers before becoming a white dwarf. These stars can be surrounded by dense envelopes of gas and dust, which obscure their light. That might explain the long, deep fades and infrared excess. But again, no clear post-AGB spectral signature has been observed in V529. No strong emission lines. No evidence of rapid evolution in color or luminosity. There is also the possibility of an edge-on dusty disk, a disk of material surrounding the star, tilted just right so that it can obscure the star periodically. This is thought to be the cause of variability in some young stellar objects, and even some main sequence stars with planet-forming disks. But this model also predicts certain thermal emissions and regular occultation patterns, which V529 has not shown conclusively. At this point, we're left with a star that, while definitively variable, defies classification. It's not a pulsating variable. It's not a binary eclipsing system. It's not clearly a young star, an old star, or a symbiotic system. Its location offers no easy answers. Its light curve mocks our attempts at periodic analysis. Its behavior is too extreme for most known models and too inconsistent for those that might otherwise apply. In a strange way, V529 Orionis is beginning to resemble a new subclass of stellar object, one not yet named, but quietly forming in the gaps left behind by other definitions. It may one day belong to a group of stars that we currently overlook simply because they don't fit our expectations. These ghost variables, for lack of a better term, may be more common than we think, stars that fade not with the regular rhythm of pulsation, but with the strange silences of hidden dust, chaotic mass loss, or unstable internal mechanisms. There's even the tantalizing idea that V529 represents an evolutionary phase we've simply not caught before. Something fleeting. A short-lived stage that bridges two known types but mimics either. What if we're seeing a star in transition, not young, not dying, but changing in ways we haven't modeled yet? This possibility is what gives V529 its edge, not just as a curiosity, but as a possible window into unknown stellar physics. It challenges us to expand our definitions, to refine our models, and to remain open to the idea that the universe still harbors types of stars we have yet to properly understand. And so we catalog it, awkwardly, uneasily, with a question mark in the column where type should go. We mark it as a variable, sure. But we also mark it as unknown. Because even now, after all the data and scrutiny, we still don't know what V529 Orionis truly is. Among the many theories proposed to explain the baffling behavior of V529 Orionis, the one that has gradually emerged as the leading contender, though not without its own complications, is the idea of dust obscuration. This is the concept that the star's bizarre variability, its plunges into near-total darkness, and its sudden, seemingly untriggered reappearances might all be the result of thick clouds of dust passing between us and the star. In other words, V529 might not be disappearing, its light might simply be getting blocked. This theory isn't outlandish. Dust plays a major role in many stellar mysteries. From the formation of stars and dusty nebulae to the dimming of supernovae light as it travels through the interstellar medium, dust is a pervasive force in the cosmos. It absorbs, reflects, and scatters light, particularly in the optical range. In some cases, it can completely obscure stars from view, even when they are physically luminous and intact. The Orion region, where V529 resides, is no stranger to dust. The entire constellation is riddled with gas and dark clouds, the remnants of generations of stellar formation and destruction. The Orion molecular cloud complex is one of the most active star-forming regions in the nearby galaxy. As a result, stars in this part of the sky are often embedded in, or positioned behind, vast curtains of interstellar material. This makes the idea that V529 might be behind or within such a dust cloud quite plausible. But with V529 Orionis, the story is likely more complicated than just a background dust screen. If interstellar dust between Earth and the star were solely to blame, we would expect the obscuration to be relatively stable or to affect nearby stars in the same region. Yet we don't see that. Stars close to V529 in the sky remain steady and visible. The obscuration seems to be targeting V529 with unsettling precision. That makes interstellar dust alone an insufficient explanation. This leads us to the idea of circumstellar dust, material that surrounds the star itself. Many stars, especially those in late evolutionary stages, begin to shed mass in the form of gas and dust. This expelled material can accumulate into a shell or disk around the star. If that structure is dense or asymmetric, and if it shifts or thickens over time, it can cause the star's brightness to change dramatically as it becomes obscured from our line of sight. In this scenario, V529 might be surrounded by an irregular dust shell that occasionally drifts or flares into view, blocking the star's light. It could also have a warped disk, perhaps formed from earlier outflows or binary interactions, which slowly rotates or pulsates, periodically aligning in a way that eclipses the star's core brightness. These obscuration events wouldn't necessarily be periodic, especially if the dust is turbulent or loosely organized. The strongest support for this theory comes from infrared observations. Dust, while nearly opaque to visible light, glows faintly in the infrared as it absorbs energy and re-emits it at longer wavelengths. Several infrared sky surveys, including two MASS, WISE, and IRAS, have at times detected an excess of infrared emission from the coordinates associated with V529 Orionis. This excess suggests the presence of warm dust, possibly in a circumstellar environment. Though not always consistent or strong enough to yield a definitive dust model, these infrared signals hint at something dusty, and warm enough to glow faintly, surrounds the star. More interestingly, these emissions sometimes fluctuate, which may correspond to phases when the star is becoming enshrouded or when dust is dissipating. These subtle variations in the infrared could be V529's indirect signature, like a shadow moving behind a curtain, leaving only a glow to tell us it's still there. A similar phenomenon is observed in our coronae borealis stars, which dim unpredictably when carbon-rich dust forms in their outer atmospheres. But as discussed earlier, V529 differs in many critical ways. It fades more deeply and stays dim for longer stretches. This raises the question, if V529 is undergoing dust obscuration, is it doing so in a way we've never seen before? One hypothesis suggests that the dust surrounding V529 might not be evenly distributed. It could be clumpy, with dense regions that drift into the line of sight. It could even be in the form of cometary fragments, or debris clouds resulting from past mass ejections. These clouds might orbit the star or linger nearby, periodically moving into a position where they block most or all of its light. Because such structures would not be uniform or symmetrical, they could create irregular dimming patterns, exactly what we see in V529's erratic light curve. Another possible explanation involves a dust disk seen edge-on. If V529 possesses a thick, opaque disk of material, possibly the remnant of an earlier mass loss event, or even the sign of planetary system formation. It could be oriented in such a way that parts of it pass in front of the star as it rotates, or wobbles. Even small changes in angle could cause dramatic fluctuations in visibility from our point of view. Stars like UX Orionis show similar behavior, with sharp fades attributed to circumstellar disks blocking the light. If this is the case for V529, then its disappearing acts might be caused by slow, complex movements in its dusty environment. This would also explain the non-periodic nature of its variability. If the disk or shell is uneven and evolving, the fades would not occur on any strict schedule. They might depend on chaotic internal dynamics or subtle changes in viewing geometry. The dust obscuration model also explains why the star returns to visibility without any explosive outbursts. If the variability were caused by stellar eruptions or mass transfer, we'd expect some sign of energetic events, shock waves, emission lines, sudden color shifts. But V529 often reappears quietly, with no evidence of such activity. That's consistent with the idea that the light was simply hidden, not extinguished. The star never stopped shining, it was just veiled behind a transient curtain of cosmic dust. And yet, despite all this, we must admit that the dust theory remains unproven. We don't yet have high-resolution spectroscopy of the star during a visible phase. We don't know the composition, distribution, or origin of the suspected dust. And the irregularity of the fading patterns makes it hard to predict the next disappearance, and harder still to aim instruments at just the right moment to catch the phenomenon in the act. What we need is time, patience, and more data. Continuous infrared monitoring could reveal more about the temperature and structure of the dust. Polarimetry, a technique that measures the alignment of light waves, could detect scattering effects associated with dust grains. High-resolution imaging might one day resolve the dusty environment itself. Until then, the dust remains both a veil and a clue. It's a poetic irony. The very substance that may be concealing V529 from view could also be the key to revealing its secrets. The dust that makes it vanish might, in time, help us finally see. The moment V529 Orionis was confirmed as a real, dramatically variable star, comparisons to known types were inevitable, and perhaps the most compelling parallel, at least initially, was with the enigmatic class of stars known as Arcturoni borealis, RCRB, variables. These stars, like V529, have long been known for their eerie ability to suddenly vanish from the sky, dimming by several magnitudes and remaining obscured for weeks, months, or even longer before gradually re-emerging. For many astronomers, the similarity was too strong to ignore. Could V529 simply be an unusually extreme or atypical example of an RCRB star? At first glance, the comparison seems not just reasonable, but even likely. RCRB stars are rare, hydrogen-deficient, carbon-rich supergiants that undergo unpredictable, dramatic declines in brightness. The mechanism behind this behavior has been studied extensively. Every so often, these stars eject small puffs of carbon-rich material, which condense into soot-like dust clouds. When one of these dust clouds happens to drift into our line of sight, it can obscure most or all of the star's visible light. The result is a sudden and deep dip in brightness. Over time, the dust dissipates or drifts away, and the star brightens once again. This pattern, seemingly random in timing, dramatic in scale, and reversible without evidence of intrinsic stellar death, describes V529 Orionis almost perfectly. The magnitude of the fading, the duration of invisibility, the quiet reappearance. All of it echoes the well-documented behavior of RCRB stars. What makes RCRB stars even more compelling as a comparison is that their unpredictability has made them something of a mystery for generations. They don't pulsate in neat, repeatable cycles. They don't follow orbital mechanics. Their bright-to-faint transitions are sudden, sometimes occurring in just a few days, while their returns to normal brightness can take weeks or months. Some spend years in obscurity. And each star in the class seems to have its own peculiar rhythm. Yet when astronomers began probing deeper into the possibility that V529 might be an RCRB star, cracks began to appear in the theory. Because despite the surface-level similarities, V529 has traits that set it apart from the classic RCRB model, and these differences are more than cosmetic. To begin with, the spectral fingerprints don't line up, at least, not from what little data we've managed to gather. RCRB stars have very distinctive spectra. They're hydrogen-deficient and carbon-rich, meaning they lack the strong hydrogen-Balmer lines that most stars exhibit, and instead show prominent bands from carbon molecules like C2 and CN. When astronomers have managed to observe V529 during its brighter phases, these spectral signatures have not been clearly identified. In fact, the spectral profile of V529 appears either featureless or too faint to analyze with confidence, which in itself is an issue. Either V529 lacks the defining molecular bands of an RCRB star, or it's so dim and variable that even during its visible phases, it doesn't reveal its true chemical nature easily. Then there's the matter of variability, timescale, and depth. RCRB stars do dip dramatically in brightness, often by 4 to 8 magnitudes, but they rarely vanish entirely. Even during their dimmest phases, they typically remain detectable with sensitive equipment. V529, on the other hand, has been reported as completely gone, absent from both visual observations and CCD data for extended periods. Not just dimmed, but erased. That level of obscuration suggests either a more opaque dust formation process, a denser cloud of circumstellar material, or possibly a completely different mechanism altogether. While RCRB stars obscure themselves with dust, their dust seems to be more transient, less total. V529's dust, or whatever is causing the fading, seems to be more efficient at rendering the star invisible. Another important distinction is location and population type. RCRB stars are thought to be old, evolved stars, often associated with the galactic halo and bulge populations. They are rare, and they're not typically found in active star-forming regions. V529, however, is located in Orion, a vibrant star-forming region rich in young stars, nebulae, and gas clouds. This would be an unusual place to find a classic RCRB star. It raises the possibility that V529 is not an aged carbon star at all, but something else, either a younger star enshrouded in material, or a post-AGB object masquerading as an RCRB analog. Yet the most curious difference, and perhaps the hardest to explain, is the degree of unpredictability. While RCRB stars fade irregularly, they tend to follow certain broad statistical behaviors. Their dips are separated by intervals that, while not periodic, have some consistency. There's usually a recovery phase that's somewhat predictable. V529, however, appears to resist even those loose patterns. Its dips come without warning, stay for erratic durations, and return without consistent slopes. Some fades are sharp and sudden, others are gradual. Some returns are quick, others take years. In short, if V529 is an RCRB star, it is the most unruly and chaotic one yet discovered. There's also the question of mass loss signatures. RCRB stars eject material regularly, and this creates detectable infrared excesses, emission lines, and sometimes even dust shells visible in high-resolution imaging. While V529 has shown hints of infrared excess, it lacks the strong IR signal and surrounding nebula that many well-studied RCRB stars display. This could mean that if V529 is related to the RCRB class, it exists on a different evolutionary path, or it is undergoing a more subtle, perhaps one-time obscuration event. Some astronomers have even suggested that V529 could represent a kind of RCRB imposter, a separate class of dust-obscured variable stars that mimic RCRB behavior but originate from different processes. Perhaps it's a post-AGB star in a transitional phase. Perhaps it's a binary with complex dust dynamics. Or maybe it's a type of massive star undergoing an unstable pre-supernova phase we haven't documented yet. In this view, RCRB stars and stars like V529 are part of a wider family of irregular variables that share dust as a key mechanism, but differ in their evolutionary histories and stellar structures. So where does that leave us? The comparison to our Corona Borealis stars is still useful. It gives us a framework, a way of understanding how stars can obscure themselves without dying. But it's also clear that V529 Orionis isn't simply another member of that rare group. Its behavior is more extreme, its location more unusual, its variability more defiant, and its cause still more elusive. In many ways, V529 might be the first of a new subclass, or the most extreme edge case of an existing one. Perhaps it's an RCRB cousin that never quite made it into the family. Or maybe it's a stellar chimera, bearing traits of different types, yet resisting every label we try to attach. And this is what makes it so important. Because for every RCRB star we've classified, every variable we've cataloged and named, there are outliers like V529, stars that break the rules, stretch the definitions, and expand our understanding of what stars can do. Even though the initial comparisons to our Coronae Borealis stars provide a useful starting point, it quickly becomes clear that V529 Orionis doesn't just stretch the mold, it breaks it. The differences aren't subtle quirks. They're profound, and they reveal just how little we truly understand about what's happening around this flickering mystery in Orion's sword. V529 may resemble our RCRB variables in its dramatic fades and occasional returns, but its irregularity, erratic timescales, and inconsistent behavior make it an outlier even among outliers. For starters, the depth of its dimming is far more extreme. Our RCRB stars often drop between 5 to 8 magnitudes during their fainting spells, and while that's dramatic, it usually leaves the star at least marginally detectable in high-sensitivity photometric data. V529, however, has exhibited fading events so deep that it becomes completely invisible, even to sensitive CCD arrays used by survey telescopes. It's not just that it dims, it vanishes. Gone. As if someone flipped a switch. This isn't just semantic. The implication of a star vanishing below the detection limit isn't simply that it's very faint. It means something is either absorbing or redirecting nearly all of the light in the visible spectrum. The physical process responsible would have to be far more efficient than the usual carbon dust clouds seen in our RCRB events. Either the obscuring dust around V529 is vastly thicker, more opaque, or differently structured, or something entirely different is at play. And then there's the timescale problem. Our RCRB stars typically show a fairly consistent pattern. Sudden dimming events that occur over days to weeks, followed by gradual brightening over months. These cycles, while not periodic, fall within a relatively narrow window of behavior. V529 cycles, if they can be called that at all, are wildly unpredictable. Some fades seem to occur gradually over long periods, others happen abruptly. Some bright phases last for months, others for only days or weeks. There's no rhythm, no cadence, no mathematical regularity. This isn't a heart beating, it's a storm raging in total chaos. Attempts to plot V529's light curve over time reveal a landscape of jagged cliffs, sudden drops, plateaus of darkness, and hesitant returns. It resists fitting into any model that assumes even a loose periodicity. This kind of irregularity suggests that whatever is causing the dimming events is not following any orbital path or regular cycle, as might be expected from dust disks or binary eclipses. Instead, it seems to follow its own internal weather pattern, driven perhaps by turbulent mass loss, rogue dust ejections, or dynamic instabilities we haven't yet encountered in other stars. Then there's the duration of invisibility. Our RCRB stars can remain obscured for weeks to months, occasionally for a year or more, but typically they return to visibility within a time frame that correlates to the dissipation of the dust cloud. V529, however, has remained undetectable for years at a time. In some stretches of historical data, it disappears from all records, photographic, digital, and observational, for extended periods. There are epochs where it appears to have ceased existing altogether, only to later flicker back into being as if nothing had happened. This prolonged silence raises an intriguing possibility. The obscuration events in V529 may not be individual clouds drifting across the star, but wholesale transformations in the star's immediate environment, perhaps enormous, thick dust formations that develop over time and envelope the star completely, then dissipate irregularly. If so, the behavior of V529 may be akin to weather on a truly titanic scale, solar systems worth of dust swirling and collapsing unpredictably, blocking light not just momentarily, but for entire observational generations. The lack of symmetry in its fading and brightening events also sets it apart. In many variable stars, whether pulsating giants, eclipsing binaries, or RCRB stars, the transitions into and out of dimming events have a broadly symmetric quality. A star dims quickly and brightens slowly, or the reverse. There's a pattern, even if subtle. With V529, no such pattern is evident. It may fade slowly and reappear suddenly, or vice versa. It may hover just above detection threshold before plummeting, or vanish abruptly with no warning. This asymmetry points again to a mechanism that is not governed by orbital timing or stable physical processes, but by chaotic, stochastic phenomena. And finally, we must consider the environmental context. RCRB stars are generally found in older stellar populations, and are understood to be in a rare, late evolutionary phase. They exist primarily in the halo or bulge of the galaxy, and their rarity is part of what makes them so fascinating. V529, by contrast, sits in Orion, a young, dynamic, and active star-forming region. If V529 were truly a classic RCRB star, it would be a bizarre interloper in this setting. Its presence here doesn't make sense, unless we're dealing with a star that only mimics RCRB behavior, but is following an entirely different evolutionary path. This has led some astronomers to speculate that V529 may represent a convergent phenomenon, where different types of stars, under different conditions, end up exhibiting similar behavior for entirely different reasons. In this view, V529 may look like an RCRB variable, but the underlying mechanism may be completely different, perhaps a young or mid-age star undergoing episodic mass ejections, or a binary system with dynamic interactions, or even a preplanetary nebula phase that mimics dust-driven fading. Some have even floated the possibility that V529 represents a new subclass altogether, a previously unidentified type of dusty variable, one that emerges only under very specific, rare conditions. If this is true, V529 may be a prototype for a family of stars we've only just begun to recognize. Others like it could be hiding in our data, written off as statistical noise, or buried in regions of the sky too crowded or dusty to study in detail. The lack of high-quality spectra during its various phases continues to handicap efforts at categorization. During bright phases, it's just luminous enough to permit low-resolution spectroscopy, but not always long enough to perform detailed studies. During faint phases, it's nearly impossible to capture anything useful. Without a continuous stream of spectral data, the star's true nature remains obscured, as elusive as the light it so often hides. What we're left with, then, is something that looks like an RCRB star, behaves more erratically, resides in the wrong neighborhood, and refuses to play by the rules. It is like a shadow cast by a familiar object, but the shadow shifts shape and defies every attempt to trace it back to its source. In the world of astronomy, such rule breakers are precious. They force us to question what we thought we knew. They illuminate the edge cases, the blurry zones of classification where new physics often lies waiting to be uncovered. V529 Orionis is a mystery not because it is completely alien, but because it almost fits, and yet doesn't. It dares us to refine our definitions, to revisit our models, to expand the taxonomy of stellar behavior. It is a reminder that the sky still holds secrets, and that even in the well-mapped regions of famous constellations, stars can still vanish, and with them, the certainty we thought we had. If we follow the trail of clues left by V529 Orionis, the erratic dimming, the suspicion of circumstellar dust, the strange, almost spectral behavior, one compelling possibility emerges that reaches deep into the star's possible life cycle, that V529 Orionis might be a candidate for post-asymptotic giant branch, Post-AGB, evolution. This is a fascinating and rare stage in stellar life, one where stars undergo profound internal and external changes, shedding their outer layers and entering a twilight phase on the path to becoming a white dwarf. And like all transitions in nature, it's often messy, irregular, and cloaked in mystery, much like the behavior we observe in V529 Orionis. To understand this possibility, let's revisit what the asymptotic giant branch, or AGB, actually is. The AGB phase occurs late in the life of low to intermediate mass stars, those between about 0.8 to 8 solar masses. These stars, having exhausted the hydrogen and helium in their cores, expand dramatically into red giants. During this phase, they become highly luminous, unstable, and begin to pulsate and lose mass in large quantities. Their outer envelopes swell, cool, and are often blown away by intense stellar winds. Much of that material condenses into thick, dusty shells that surround the star, sometimes forming complete circumstellar cocoons. Eventually, after enough mass has been lost and the star can no longer sustain fusion in its outer layers, it begins to contract again. This is where the post-AGB phase begins, a brief, turbulent chapter between the red giant stage and the final transformation into a white dwarf. During this phase, the star is typically enshrouded in its own cast-off material. The remaining core heats up rapidly, potentially ionizing the surrounding gas and forming a planetary nebula. But before that happens, there is often a phase of profound obscuration, instability, and irregular luminosity. That's the key. The post-AGB phase is a transitional twilight, not steady, not well-behaved, and not yet fully understood. And stars in this phase can sometimes mimic all the symptoms we observe in V529 Orionis. One of the main characteristics of post-AGB stars is that they're surrounded by dense, dusty envelopes or disks, formed from the material ejected during the AGB phase. These shells can obscure the central star completely depending on their geometry and density. In some orientations, especially when the system is viewed edge-on, the central star might be blocked entirely from optical view for long periods. Only the scattered light, or thermal emissions in the infrared, can reveal its presence. This could explain the deep, prolonged dimming episodes of V529 Orionis. If the star is indeed in a post-AGB phase and surrounded by a non-uniform, evolving shell of gas and dust, then the obscuration we see might not be due to episodic dust ejections, but rather to a pre-existing, complex circumstellar environment. This dusty cocoon might shift, settle, or thicken in certain areas, occasionally drifting into our line of sight and blotting out the star. Some post-AGB stars are known to show variable behavior in both optical and infrared wavelengths. Their irregular light curves are often attributed to changes in dust opacity, to variable mass loss, or to interactions with unseen binary companions. Some post-AGB objects even pulsate during this phase, though typically with longer and smoother rhythms than V529 shows. That said, every star is unique in this phase. Because the post-AGB stage is short-lived and chaotic, it's a moving target for astrophysical modeling. Interestingly, several known post-AGB stars do exhibit similar erratic fading behavior. Take for instance the so-called protoplanetary nebulae, objects like the red rectangle or the egg nebula, where the central star is heavily obscured by dust and only visible through scattered light. These systems often show unexpected dimming and brightening events, sometimes related to internal disk dynamics, binary motion, or variable mass loss. If V529 Orionis is such a system, we might be catching it at an incredibly rare moment, just after the red giant phase, but before it becomes a glowing planetary nebula. A stage that could last mere thousands of years, a blink in stellar terms. If true, then V529 might be a celestial chrysalis, no longer what it once was, and not yet what it's going to become. Support for this theory also comes from the infrared excess that has occasionally been detected from V529's coordinates. Post-AGB stars tend to emit significant infrared radiation because of the warm dust in their surroundings. The dust absorbs the star's light and remits it in the infrared, creating the telltale signature of circumstellar obscuration. V529 has shown variable IR excess in past surveys, possibly a sign of a shifting dusty shell around an evolving core. Another clue lies in the lack of hydrogen lines in the spectrum, though this evidence is tentative due to the difficulty of capturing clean spectroscopic data. Post-AGB stars, like RCRB stars, often show signs of hydrogen deficiency, either because they have burned through their hydrogen layers or because of unique chemical processes that occur during late-stage evolution. V529's spectrum, when observable, has at times appeared oddly featureless or difficult to classify, potentially aligning with this idea. There's also the tantalizing idea that V529 could be a binary post-AGB system, in which the central star is interacting with an orbiting companion, possibly a white dwarf or a lower-mass star. Such systems often have stable circumbinary disks, where dust collects in a toroidal structure around both stars. These disks can produce unpredictable extinction events if they're tilted relative to Earth. And because the post-AGB phase is short, we might be witnessing a narrow evolutionary window in which the central star and its companion are sculpting the dusty environment together in complex, dynamic ways. But as always with V529, evidence is elusive. There has never been a definitive detection of a binary companion. No obvious radial velocity shifts have been observed, though it's possible that any companion is faint, cool, or tightly bound in a way that hides it from standard detection methods. A faint white dwarf or substellar object could be hidden within the dusty veil, subtly influencing the structure of the obscuring shell without revealing itself through conventional means. And we must be cautious not to overinterpret the similarities. Many post-AGB candidates exhibit clearer evolutionary markers, such as strong infrared spectral features, high luminosity pulsations, and identifiable planetary nebula precursors. V529 has not been definitively linked to any such phenomena. There are no known emission nebulae nearby. No dramatic outflows have been detected. No clear bipolar lobes, as seen in some transitional stars. If it is post-AGB, it may be one of the quietest, most stealthy examples ever recorded. Still, the post-AGB hypothesis offers something other models struggle to provide: a natural explanation for the erratic obscuration, the dusty circumstellar environment, the mid-infrared excess, and the erratic light curve, all as symptoms of a dying star attempting to shed its outer shell. It allows for irregular behavior. It embraces instability. It frames the vanishing light not as an anomaly, but as a byproduct of metamorphosis. In the end, if V529 Orionis is indeed in the post-AGB phase, then we are witnessing a deeply private transformation. A star letting go of the outer layers it once radiated proudly. A life collapsing into lightlessness. A core heating up beneath a dusty shroud, preparing to cast off the veil in a final act of celestial creation, a planetary nebula. But until then, we see only hints. A flicker. A ghost. A vanishing star trying to become something else. If there's one theme that repeats itself in the story of V529 Orionis, it's concealment. This is a star that hides, that fades, that teases observers with its elusiveness. And whenever a star seems to disappear without an obvious explanation, astronomers inevitably ask the question, is it alone? Could V529 Orionis actually be part of a binary system, with an unseen companion periodically, or irregularly, passing in front of it or interacting with it in such a way that causes these deep and puzzling dimming events? The idea isn't just convenient, it's grounded in precedent. Many variable stars owe their variability not to their own internal processes but to interactions with companion stars. Eclipsing binaries, in particular, are a well-studied class. In these systems, two stars orbit a common center of mass, and from our vantage point, one sometimes passes in front of the other. This causes a measurable drop in brightness, like the regular blinking of a lighthouse. In ideal conditions, these eclipses happen with clockwork precision, allowing astronomers to model the masses, sizes, and orbits of the stars involved. But V529 Orionis doesn't play by those rules. If it is part of a binary system, it would have to be one of the strangest binaries we've yet encountered. The first challenge is irregularity. The light curves of classic eclipsing binaries show predictable dips, corresponding to the orbital period. These dips might vary in depth depending on the star's sizes and temperatures, but they usually follow a consistent pattern. V529 shows no such regularity. Its fading episodes do not appear on a schedule. Some occur close together, others are separated by years. The duration of the dimming is unpredictable, and the return to brightness is often asymmetric. If these events are eclipses, then they must be governed by something far more complex than simple orbital mechanics. One proposed solution is that V529 is part of an interacting binary system where the companion is not just orbiting, it's actively altering the star's environment. Perhaps the companion is embedded in or orbiting within a thick dust disk or envelope surrounding V529. As it moves, it could stir up clouds of dust, or even eject material itself, leading to localized obscuration. In this scenario, we wouldn't be seeing eclipses in the traditional sense. Instead, the companion could be disturbing a dust disk, like a spoon stirring smoke, resulting in clouds of material drifting into our line of sight. Some systems like this are known. The famous binary system Epsilon Orionis, for example, exhibits periodic dimming caused by a massive, opaque dust disk surrounding a secondary object. The primary star is a luminous F-type supergiant, and the companion is thought to be a B-type star enshrouded in a dark, tilted disk. Every 27 years, this disk eclipses the primary star, causing a multi-year dimming. If V529 Orionis is a similar case, it would explain the long, and sometimes total fades, though in V529's case, the timing seems far more erratic. Alternatively, the companion might not be obscuring the light directly, but triggering mass ejections or dust production in the primary star through gravitational interaction. Imagine a tight binary system where the two stars approach each other closely at certain points in their orbit, say, a highly elliptical orbit where they're far apart most of the time but come close together periodically. These periastron passages could gravitationally stress the primary star, causing it to shed material or eject carbon-rich dust clouds. These clouds could then drift into our line of sight, obscuring the star and causing the deep fading events we observe. If the orbit were irregular due to additional bodies or a poorly understood resonance, the timing of these events could be as chaotic as V529's light curve suggests. It's even possible that the orbit is decaying or being altered by mass loss, introducing further unpredictability. Another possibility is that the companion itself is surrounded by dust, or perhaps it's a cool, low-mass star, or even a brown dwarf, that brings its own material into the system. If this companion has a disk or dusty envelope of its own, it could cast shadows across the system or contribute to the overall obscuration. Such a companion would be incredibly hard to detect directly, especially if it emits little light of its own and is lost in the glare or dust of the primary. So far, no direct evidence of a companion star has been observed. Radial velocity measurements, which can detect the gravitational wobble of a star due to an orbiting partner, are extremely difficult with V529. The star is usually too faint to capture precise spectra, and during its visible phases, it is often observed for too short a duration to accumulate meaningful data. We don't yet know if there's a telltale shift in spectral lines indicating an orbital partner. But that doesn't rule out a companion. It only reveals how difficult it is to study such a faint and intermittent target. If there is a companion, one potential observational clue might be the infrared excess occasionally seen from V529. A faint, cool object, like a brown dwarf or dust-shrouded star, might emit primarily in the infrared. Some past surveys have noted excess mid-infrared flux near V529's coordinates, though the data are sparse and the signal weak. Still, if this excess can be tied to a secondary object, it would help explain both the source of the dust and the mechanism for its irregular behavior. The theory of a binary system becomes more tantalizing when we consider the possibility of circumbinary disks. Disks of material that surround both stars in a binary pair. In such systems, gravitational resonances between the two stars can create gaps, spirals, and asymmetries in the disk. These structures can shift over time, drifting in and out of our line of sight, sometimes blocking the light of the stars. A warped or precessing circumbinary disk could periodically obscure the central region, explaining the unpredictable fades of V529 without invoking direct eclipses. Such systems have been observed in pre-main sequence stars like those in the KH-15D system, where a warped circumbinary disk causes complex, changing eclipses that evolve over time. While V529 isn't a young star, or at least isn't assumed to be, similar dynamics could apply in a more evolved system with residual or regenerated dust. It's also possible that we're dealing with a hierarchical system, where V529 has not one, but two or more companions, perhaps a tight inner binary and a distant third star, or a small group orbiting a common center of mass. These kinds of systems are inherently unstable, and gravitational interactions between the components could lead to periodic dust formation, dynamic instability, or chaotic orbital behavior. This would complicate light curves, making periodicity almost impossible to detect without long-term, precise monitoring. In any of these scenarios, the key idea remains the same: the fading of V529 Orionis may not be entirely due to its own internal processes. It may be the result of interaction, gravitational, material, or magnetic, with an unseen partner. And like dancers cloaked in shadow, these interactions play out behind a veil of dust, hidden from our direct view, but betrayed by the rhythm of the vanishing light. If we ever manage to catch V529 in a prolonged bright phase, a dedicated spectroscopic campaign could begin to search for Doppler shifts, or perhaps subtle asymmetries in the spectrum that suggest a blended source. Adaptive optics or high-resolution imaging might one day isolate a faint companion, and continued infrared observations could reveal the thermal fingerprint of a hidden partner star or its surrounding disk. Until then, we are left with a compelling question and no easy answer. Is V529 Orionis alone in the dark? Or is its light being swallowed by a companion whose presence we have yet to see, but whose influence we already feel? The story of V529 Orionis becomes even stranger when we move beyond the visible spectrum and into the realm of infrared. If the optical observations of V529 reveal its ghost-like tendencies, fading, vanishing, flickering in and out of existence, then the infrared observations whisper an entirely different tale. A tale of heat, of hidden warmth, of a star that, while dim to the human eye, continues to glow in wavelengths we cannot see. This is where we encounter what astronomers often refer to as infrared excess, a telltale signature that something around the star is absorbing visible light and re-radiating it as heat. And in the case of V529 Orionis, multiple surveys over the years have detected just such an excess. Not a massive one. Not the kind you'd associate with a young, planet-forming system or a flaming red giant. But enough to raise eyebrows. Enough to hint that the invisibility of V529 might be less about its death, and more about its disguise. Let's break this down. A typical star emits most of its energy in the visible and ultraviolet regions of the electromagnetic spectrum. Its brightness across different wavelengths follows a curve that corresponds to its surface temperature. This is called a blackbody curve. If a star has no nearby dust, gas, or planets, its emission tapers off in the infrared in a smooth, predictable way. But when dust is present, that pattern changes. Dust near a star absorbs some of the star's radiation, particularly in the ultraviolet and visible ranges, and heats up. Then, it re-emits that energy in the form of infrared radiation. This creates an infrared bump in the emission profile, an excess of energy in the IR region of the spectrum that cannot be explained by the star's surface temperature alone. This is exactly what we've seen, sporadically, and tantalizingly, from V529 Orionis. Various infrared sky surveys, including two MASS, WISE, and IRAS, have scanned the region around Orion's sword, capturing data on thousands of stars and dust clouds. In the specific coordinates corresponding to V529, astronomers have occasionally identified a mid-infrared source with excess flux, more infrared energy than the star should produce on its own. Not bright enough to stand out strongly among the hot stars of Orion, but anomalous enough to be flagged in follow-up studies. The infrared signal is not always easy to isolate. Orion's sword is a notoriously crowded part of the sky, rich in star formation, bright emission nebulae, and complex dust filaments. The nearby Orion Nebula, M42, itself emits strongly in infrared, and distinguishing one faint variable star from the diffuse IR glow of the surrounding region is a significant challenge. Nonetheless, several detections do suggest a persistent, if faint, infrared source at or near the location of V529 Orionis. This suggests a surrounding environment composed of warm dust, perhaps a circumstellar disk, or even a toroidal shell, absorbing the star's visible light and glowing gently in the heat spectrum. What's fascinating is how this aligns with the star's behavior. A dust disk could explain the deep and irregular dimming events. As regions of the disk rotate, clump, or shift, they might obscure the star at random intervals, cutting off its visible light while leaving the infrared mostly unaffected. Depending on the composition and grain size of the dust, certain wavelengths might pass through while others are absorbed or scattered, creating the complex variability we observe. This model also allows for asymmetrical obscuration, where one side of the star is blocked while the other remains exposed, or where we see light scattered around dense dust blobs. The result would be a light curve that's not just erratic in timing, but in depth, shape, and color, all of which have been reported in various observations of V529. There's even more support for this from comparisons to other stars with known dusty environments. Post-AGB stars, young stellar objects, and evolved binaries with dusty companions all show similar IR excesses. And in many of those systems, the dust is not evenly distributed, but forms complex structures, warped disks, bipolar lobes, equatorial rings. These structures can change over time, expanding, fragmenting, precessing, causing the kind of irregular, prolonged dimming events that V529 is known for. Then there's the question of thermal timescales. Dust doesn't heat or cool instantly. Depending on its distance from the star, composition, and density, it can retain heat long after the star fades from view. This means that even during V529's invisible phases in the optical, the infrared excess might persist, glowing gently from the stored warmth of previous radiation. That would explain why IR surveys can still detect a signal even when no visible star is apparent. But there are challenges. For one, the IR excess is not constant. It appears in some observations and not in others. This could be due to several factors: observational limits, variability in dust production, or changes in viewing angle. Alternatively, the dust might be transient, forming in clouds that dissipate over time, or orbiting in such a way that we only detect them when they are heated directly or drift into view. Another possibility is that the dust is being periodically replenished. If V529 is shedding mass in brief outbursts, then each fade could correspond to a new layer of dust being cast off and briefly heated. These short-lived dust events would be difficult to catch without continuous monitoring but could leave behind a detectable IR trail in the weeks or months that follow. There's also speculation about non-stellar contributions to the IR signal. Could V529's infrared emission be partly from circumstellar material accreting onto a companion? Or from collisions within a debris disk, perhaps stirred by an orbiting planet or binary interaction? These ideas are harder to support without more data but remain on the table as astronomers struggle to make sense of the inconsistent IR footprint. What's frustrating and exhilarating is how little we truly know. The current infrared data on V529 is incomplete. No long-term infrared light curve exists. No high-resolution mid-IR imaging has been done to map the dust. Most of what we have are scattered points from sky surveys, enough to suggest the presence of a warm, dusty environment, but not enough to model it definitively. Yet even these faint whispers in the infrared provide clues. They tell us V529 is not alone in the cold. That something surrounds it. That even in its darkest phases, it's not dead, it's hidden, wrapped in warmth and shadow. That when it vanishes from our sight, it doesn't disappear from existence. It continues to shine quietly, just beyond the limits of our unaided eyes. And perhaps that is the most haunting truth of all. That some stars don't die. They don't collapse or explode. They simply drift behind a curtain of dust. They whisper in heat, not in light. And they wait, unknowable, just outside our reach. If the flickering, vanishing behavior of V529 Orionis could be seen as a kind of cosmic drama, then the theory that it may be evolving into a protoplanetary nebula introduces an extraordinary act in that unfolding story. It offers a possibility that is not merely technical or observational, but one that is deeply transformative. Because if this theory holds, then what we're witnessing isn't just irregular dimming or stochastic variability. We are watching a star in the process of dying, but doing so in a way that is creating something new. We may be seeing the prelude to one of the most visually stunning and mysterious phenomena in the sky, the creation of a planetary nebula. To explore this, let's first clarify what a protoplanetary nebula, often abbreviated as PPN, really is. Despite the name, it has nothing to do with planets. The term is a historical artifact. In modern astronomy, a protoplanetary nebula is a short-lived transitional stage between the asymptotic giant branch (AGB) phase of a star's life and the planetary nebula phase. It's that moment, cosmically brief, when a star has begun to shed its outer layers but has not yet become hot enough to ionize the surrounding material into the luminous, colorful glow we associate with planetary nebulae. This PPN phase lasts only a few thousand years, making it incredibly rare to observe. Most stars evolve through it so quickly that the number of visible candidates in the sky is small, maybe a few hundred. And even fewer are visible at all wavelengths. Many are wrapped in thick cocoons of dust and gas, making them difficult to detect except in the infrared or radio wavelengths. Their light is often obscured by their own debris, the very material they are expelling into space. Now consider V529 Orionis, a star known for disappearing, for flickering to invisibility for years at a time, for surrounding itself in a mystery of dust and darkness. The idea that it might be in this twilight transformation is not just poetic, it's plausible. What makes this theory compelling is the match between the observed behavior of V529 and the known characteristics of protoplanetary nebula progenitors. First, let's examine the mass loss behavior. Stars entering the PPN phase begin to lose their outer layers rapidly, sometimes in fits and starts. This process can generate large, complex structures of gas and dust around the star, including toroidal disks, bipolar outflows, and clumpy ejecta. The material is often expelled unevenly, forming chaotic environments. As the star loses its envelope, the core begins to heat up, but the remaining dust often obscures it from view in optical wavelengths. We may only see scattered light, or the glow from warm dust in the infrared. This aligns closely with V529's observed infrared excess and its deep, irregular optical fading. A star in this transitional phase might disappear not because it's cooling or dying completely, but because it is shrouding itself in the very material it is casting off, forming a self-made veil of dust that waxes and wanes with time. Moreover, stars in the protoplanetary nebula phase often have detached shells of dust that produce abrupt dimming when viewed edge-on or through particularly dense regions. Some exhibit behavior that mimics our Corona borealis stars, sudden, deep fades due to obscuring dust clouds, but without the same hydrogen deficiency or spectral traits. If V529 is a PPN, it might be one of these mimic systems, blurring the boundaries between known variable categories. One of the defining features of protoplanetary nebulae is their spectral ambiguity. Because they're caught in transition, their spectra can show odd combinations, features of a cooling giant, signs of increasing core temperature, and infrared emission lines from surrounding molecules or dust grains. Observations of V529 during its rare visible phases have produced weak, low-resolution spectra that are hard to classify, another tick in favor of a transitional state. Then there's the question of luminosity. Stars entering the PPN phase tend to be luminous but cool in the visible spectrum, and bright in the infrared due to dust. They also begin to develop winds, high-velocity outflows of gas that sculpt their surrounding environment. Though we don't yet have evidence of strong outflows from V529, the asymmetry in its fading and brightening might be consistent with a patchy, evolving wind-blown envelope. Even more compelling is the location of V529 in Orion, a region rich with molecular gas, young stars, and star-forming remnants. While protoplanetary nebulae are not generally expected in regions of recent star birth, they are not impossible. It's conceivable that an older population of stars exists within the complex layers of Orion's molecular cloud. V529 could be a member of an older, hidden generation that formed earlier and is now approaching the final stages of stellar evolution, its fading light buried in the shadow of a younger, brighter neighborhood. There is also evidence, albeit sparse, that some PPNs exhibit variability in their light curves, similar to what we see in V529. These variations may not always be caused by dust but could stem from pulsations in the core, changes in the density of the envelope, or dynamic structural shifts in the surrounding material. Again, V529's erratic behavior might be explained not by a single process, but by a complex layering of multiple overlapping phenomena: internal pulsations, episodic mass loss, obscuring dust, and perhaps the gravitational effects of a hidden companion. Still, the theory is far from confirmed. The primary weakness of the PPN hypothesis is the lack of associated nebular features. Most protoplanetary nebulae exhibit at least some extended emission in high-resolution images, lobes, arcs, or even faint concentric shells of gas. So far, no such features have been detected around V529. But this could be due to a combination of distance, faintness, and viewing angle. If the surrounding material is optically thick and viewed edge-on, it may be masking or blending with the background of the Orion region. If the nebula is young or still forming, it may not yet be detectable with current instruments. Another complication is timing. The PPN phase is very short on the cosmic clock, just a few thousand years. To catch a star in this phase is rare. To catch one doing so erratically, with deep fading events, in a crowded sky region, is rarer still. But the rarity of such a coincidence doesn't make it impossible, just special. And V529 has already proven itself to be an exception in nearly every way. In the end, the idea that V529 Orionis could be evolving into a protoplanetary nebula reframes everything we see. It's not simply disappearing, it's transforming. The dimming is not a death, it's a birth of sorts. A shedding. A becoming. If the theory is true, we are not just observing a star, we are witnessing metamorphosis. A once stable sun-like object discarding its outer self, preparing to light the surrounding darkness with the final, dazzling signature of its existence. What will that look like? Will the dust clear one day, revealing the hot core? Will a planetary nebula bloom around V529 Orionis, painted in blues and greens and crimson as it ionizes its own expelled layers? Or will it remain hidden, slowly fading in infrared silence, forgotten in the glow of Orion's sword? Only time, and patience, will tell. While the tale of V529 Orionis twists its way through complex theories, high-resolution instruments, and infrared anomalies, it's essential to remember where much of its story was kept alive, not in the halls of observatories or the pages of peer-reviewed journals, but in the quiet backyards and modest telescopes of amateur astronomers. In fact, much of what we know, or suspect, about V529's bizarre behavior has been preserved, tracked, and questioned thanks to the persistent efforts of those who scan the night sky, not because they're paid to, but because they can't help but look. V529 Orionis is not an especially bright star under normal conditions. Even at its peak visibility, it's on the threshold of what's easily seen with the naked eye under dark skies. And when it fades, which it often does, it dips below visibility even through binoculars, requiring modest telescopic assistance. That alone means that casual stargazers rarely notice it. But for variable star observers, those who routinely track and log fluctuations in stellar brightness, V529 has been a source of quiet fascination for decades. Many of these observers belong to global networks such as the AAVSO, American Association of Variable Star Observers, the BAVSES, British Astronomical Association's Variable Star Section, and other regional and international organizations. These groups maintain archives of brightness observations, some of which stretch back over 100 years. In these archives, V529 appears like a wandering ghost, present in one decade, absent in the next. It's not the kind of star that lends itself to flashy discovery headlines or rapid publication. Instead, it required patience, repeated observation, the kind of attention that only comes from people who know what they're looking for, and care enough to keep looking even when nothing happens for months or years. The earliest documented records of V529's odd-dimming episodes come not from space telescopes but from individuals hunched over eyepieces in cold backyards. Using visual estimates or photometric tools attached to modest gear, these observers began to notice something odd. The star that was supposed to be there simply wasn't. They double-checked. They realigned their finder scopes. They verified catalog coordinates. And still, nothing. In an era before automated sky surveys, these vanishings might have been dismissed as observational errors. Indeed, many early reports were. But as the logs grew, sometimes by hand, in notebooks, sometimes typed into early computer databases, a pattern began to emerge. Multiple observers, across different nights, using different equipment, were seeing the same thing. The star was fading, dramatically. Then, weeks or months later, it would return. It's this grassroots vigilance that ultimately kept V529 Orionis from vanishing not just from the sky, but from our awareness. If these amateur astronomers hadn't persisted, if they hadn't taken the time to file seemingly unimportant reports about a single star dimming for no clear reason, then the astrophysics community might have overlooked it entirely. There are thousands of stars in Orion alone. Without the careful watch of these dedicated individuals, V529 might have remained nothing more than a faint catalog entry, one dot among millions. The spirit of amateur contribution to science is often romanticized, but in this case, it's deserved. Observing variable stars isn't glamorous work. It's often slow, repetitive, and filled with uncertainty. But it has always played a crucial role in astronomical progress. Professionals simply don't have the time, or resources, to monitor every obscure star in the sky night after night. That responsibility, and that passion, has been taken up by amateurs for over a century. Some of these amateur astronomers became personally invested in V529 Orionis. They plotted light curves by hand. They corresponded with researchers and catalog compilers. They defended their observations when skeptics dismissed the star's behavior as equipment malfunction or atmospheric error. In more recent years, some began using CCD cameras and digital photometry, refining their observations to the point where they could detect subtle changes in brightness, pulses and dips that suggested something far more complex than a simple variable star. Online forums and mailing lists became meeting grounds for discussion about the star. Observers from Europe, North America, and parts of Asia began to compare notes, share telescope images, and alert each other when a new dimming event began. Even though V529 lacked an official variable classification for decades, it became something of a cult object among experienced skywatchers, an enigma worth watching, if only because it refused to behave. Perhaps one of the most striking aspects of this amateur involvement is that many of the dimming episodes we now associate with V529 were discovered first not by large-scale photometric surveys, but by individuals watching the sky in real time. In an age where much of astronomy is driven by automated alerts and robotic telescopes, this is a reminder that eyes on the sky still matter. That human perception, coupled with patience, pattern recognition, and curiosity, can outperform automation in areas where no algorithm was ever designed to look. Over time, some of these amateur observations were folded into larger databases. When professional observatories finally turned their attention to V529, they often relied on the long, consistent observational records built by amateurs. In fact, the case for V529's variability was strengthened immeasurably by this continuity. Decades of informal monitoring that showed a clear pattern of erratic dimming and return. To this day, V529 Orionis remains an ideal target for amateur variable star watchers. Its erratic behavior means every night of observation carries a chance, however slim, of catching the star in a new act of its mysterious play. Some observers have devoted entire seasons to monitoring it, hoping to identify the next drop in brightness, the next unexpected fade, the next clue to its nature. In many ways, the involvement of amateur astronomers in tracking V529 is not just an observational story, it's a philosophical one. It reminds us that discovery isn't always about finding something new. Sometimes, it's about noticing something strange in what's already there. Sometimes it's about persistence, about watching something until it finally changes. It's about not turning away just because nothing happened last night, or the night before. For all the data we now have from satellites and space-based observatories, we still rely on these patient observers to find what the machines miss. Stars like V529 Orionis slip between the cracks of the survey programs. They're too faint, too variable, too inconsistent to trigger alerts. But to the amateur astronomer, they are exactly the kind of mystery worth watching. And in watching, they help science see. In the darkness between stars, amid the crowd of more famous targets in Orion, a small star flickers. And in backyards around the world, a quiet network of observers waits to see what it will do next. As the strange saga of V529 Orionis unfolded over the decades, its story grew even more surreal, not just because it vanished from the sky, but because it began vanishing from the record. In a field as data-driven as astronomy, where precision and consistency are paramount, few things are more unsettling than a star that seemingly ceases to exist on paper. And yet, that's exactly what happened with V529 Orionis. In some star catalogs, this peculiar variable simply disappeared. It wasn't removed with a footnote or marked dubious. It just wasn't there anymore. This peculiar vanishing act wasn't due to neglect or oversight. It was the direct result of the star's erratic behavior. When V529 entered one of its deep dimming phases, often lasting months or even years, it dropped below the detection limits of many sky surveys. Observatories scanning the region would come up empty. Photographic plates, CCD surveys, and space-based catalogs all recorded nothing at its position, just empty sky, or perhaps faint background fuzz. And when these surveys were compiled into modern catalogs, the logic was simple. If a star doesn't appear, it doesn't get listed. Of course, most cataloging systems don't intentionally delete stars. They simply overwrite entries with the most recent data. If a source is seen in Survey A but not in Survey B taken decades later, Survey B may assume the earlier detection was noise, a transient event, or an error. In the case of V529 Orionis, this exact scenario played out multiple times. It was noted in early visual surveys, sometimes faintly, sometimes prominently, but when subsequent digital sky surveys failed to detect it, its presence in the master records became questionable. Some databases kept it with cautionary flags. Others dropped it altogether. A striking example of this was seen with early editions of the USNOB 1.0 catalog, which pulled data from decades of photographic observations. V529 Orionis was inconsistently registered depending on the plate used and the epoch of observation. On some photographic plates, it appeared clearly as a 12th or 13th magnitude star. On others, it was entirely absent. Cross-matching these inconsistencies proved difficult, especially when sky coverage wasn't uniform, and local background stars in Orion's crowded fields further muddled identification. The result? The star was listed, then unlisted. Flagged as suspect. Faded into ambiguity. Even the Simbad Astronomical Database, a central reference point for star identifiers, has struggled with the star's history. Depending on how one searches, by catalog number, coordinates, or aliases, V529 Orionis might appear under an obscure entry, or not at all. Its identity has at times been entangled with neighboring stars or misidentified due to errors in astrometric matching. More than once, researchers looking to pull its observational history have found dead ends, data points with no source, coordinates with no visible object, references to stars that don't match current images of the sky. In some ways, this catalog vanishing mirrors its physical vanishing, a kind of astrophysical camouflage, not caused by distance or speed, but by silence. A star that won't shine doesn't announce itself to the surveys. It doesn't raise its hand when the data is taken. It simply lets the moment pass, waiting in shadow. To make matters even more complicated, many of the most comprehensive stellar catalogs, like Gaia, Hipparcos, and Tycho, have strict thresholds for inclusion. Gaia, for example, is designed to detect objects brighter than roughly 20th magnitude in the optical band with extreme astrometric precision. But it also filters based on motion, parallax, and repeated observation. If V529 was invisible or unresolved during its scanning window, Gaia might miss it. If it was visible, but only briefly or during a single scan, it might be considered statistically suspect and left out of final release versions. This leads to a strange and unsettling possibility that a real star, demonstrably variable, observed and tracked by humans for decades, could fall through the cracks of the most powerful star mapping missions ever created. Not because it moved away. Not because it ceased to exist. But because it did something much stranger, it went dark. And this has real consequences. Astronomers and AI-based sky survey tools that rely on databases to generate observing lists, track transient events, or predict stellar behavior may entirely overlook V529. Software designed to flag irregular stars might never detect it because, for the system, it doesn't exist. For all the high technology involved in scanning the skies, many of our tools still depend on stable, visible reference points. V529's invisibility breaks those assumptions. This digital disappearance has even fueled skepticism about the star's behavior. For some years, there were debates in online forums and among amateur networks about whether V529 was real or a cataloging artifact. If it wasn't in the official listings, where was the proof? But in response, dedicated observers, both amateur and professional, have stepped forward with logs, images, and personal records that prove it was there. That they saw it, measured it, tracked it. That its absence from modern catalogs is not proof of its non-existence, but rather, of its irregular visibility. This raises a broader issue in astronomy. What happens when a star chooses not to be counted? When it plays hide-and-seek with our instruments, do we write it off as an anomaly? Or do we question whether our methods are built for such elusive phenomena? V529 Orionis forces us to confront the limitations of our systems, not just the telescopes and detectors, but the databases, the algorithms, the assumptions we use to filter the cosmos into something manageable. When stars don't behave like the majority, our pipelines don't always accommodate them. They get misclassified, mislabeled, forgotten. And unless someone keeps looking, keeps remembering, they can vanish, not just from view, but from the record. In a universe that's supposed to be mapped, charted, and modeled down to the arcsecond, there's something haunting about that. A star blinking in and out of being, not just to our eyes, but to our knowledge systems. V529 Orionis doesn't just vanish in light. It vanishes in data, in code, in memory. And yet, for those who know where to look, and when to look, it reappears, quietly defying the notion that everything important is already catalogued. It reminds us that the sky is not a finished product. It's a living archive. One that still hides things. It's a paradox that seems almost poetic. V529 Orionis, a star that flickers, vanishes, and eludes even the most thorough sky surveys, resides not in some obscure, forgotten region of the cosmos, but in one of the most recognized and celebrated constellations in the entire night sky, Orion. For centuries, Orion has captivated the human imagination. From ancient civilizations that carved its outline into their myths and monuments, to modern stargazers tracing its belt across the winter sky, this constellation has been a kind of cosmic landmark. And yet, nestled within its glowing sword, surrounded by some of the most observed and photographed celestial wonders, lies a star that very few have even heard of. A star that, quite literally, hides in plain sight. To understand the profundity of this, consider Orion's sword itself. Hanging below the famous belt of Orion, the sword contains the glittering jewel of the Orion Nebula, M42, a massive, brilliant stellar nursery that draws the attention of every amateur astronomer and astrophotographer on Earth. The region is teeming with light, activity, and discovery. Dozens of stars, gas filaments, dust lanes, protostars in various stages of formation. Entire generations of stars being born in waves of ultraviolet radiation. It's one of the most luminous regions in our galaxy when viewed through a telescope. And just off to the side, quiet, dim, barely holding its place, is V529 Orionis. A star with no glow, no colors, no nebular swirls. Just a faint, flickering ember that sometimes vanishes altogether, refusing to participate in the light show around it. It doesn't call attention to itself. It doesn't announce its presence. Most observers, even those deeply familiar with the sword of Orion, don't even know it's there. This contradiction is staggering. How can something be located in the most iconic constellation in the sky and yet remain so deeply obscure? The answer, in part, lies in our perception, our tendency to focus on the loud, the bright, the dramatic. M42 is bold. Bellatrix and Betelgeuse blaze. The belt stars line up with geometric precision, drawing the eye with symmetry and brightness. Against this spectacle, V529 seems insignificant. It blends into the background. And then, at times, it quite literally disappears. But therein lies its power. Its uniqueness. In a constellation defined by grandeur and luminosity, V529 Orionis stands out by doing the opposite. It dims. It retreats. It refuses to shine when expected. It's the cosmic equivalent of a whisper in a room full of shouting. It takes a different kind of attention to hear. Astronomy often teaches us that the universe is vast and full of mystery. But V529 reminds us that the unknown isn't always far away. It can be tucked between the lines of what we think we've already explored. It can be woven into the very constellations we've drawn in textbooks, studied in school, and recreated on planetarium domes. We assume, wrongly, that because we've mapped something, we understand it. V529 shatters that illusion. Its story is one of invisibility amidst familiarity. Its very existence forces us to ask deeper questions. What else are we missing in the sky we think we know so well? How many other stars flicker between visibility and disappearance, going unnoticed simply because they don't conform to expectations? How many mysteries lie embedded in the settled regions of the heavens? There's a haunting kind of elegance in this idea. That some truths only emerge when we look away from the obvious. That secrets can thrive, not in the shadows, but under the spotlight, if the spotlight is looking the other way. It also speaks to a deeper human tendency, the way we overlook things that don't draw attention. In the realm of the cosmos, as in life, there are stars, people, places, ideas, that exist quietly on the edge of our awareness. They don't flare. They don't demand. But if we take the time to notice them, we find richness and complexity we never expected. V529 Orionis isn't a supernova, or a gamma-ray burst, or a black hole tearing apart a star. It doesn't shake the galaxy or blaze across our skies. Instead, it whispers. It lingers. It fades and returns, playing its game of cosmic hide and seek in one of the most well-lit corners of our night sky. It's the anomaly that says, even here, even now, in a constellation you've seen 1,000 times, there is more to find. This makes it more than a variable star. It becomes a symbol of humility in science, a reminder that our knowledge, no matter how vast, is always incomplete. That mystery can exist not just on the fringes of the known universe, but at its very heart. And that sometimes, the most extraordinary things are those we almost never see. Zooming out from V529 Orionis reveals not a retreat from the mystery, but a plunge into a much wider, more tangled tapestry of cosmic secrets. Because Orion, as familiar and iconic as it may be, is no ordinary constellation. It is, in many ways, the sky's greatest illusion, a theater of brilliant stars arranged in a mythic shape, yet hiding a complex and chaotic story beneath its glittering silhouette. To truly grasp how V529 fits into this grand stage, we must explore what makes Orion not just beautiful, but profoundly strange. At first glance, Orion is a beacon of order. The belt, Alnitak, Alnilam, and Mintaka, sits in perfect alignment, flanked by the brilliant Betelgeuse and Rigel like cosmic cornerstones. Below the belt dangles the sword, home to M42, the Orion Nebula, and several smaller clusters and stars. For centuries, it has been a celestial landmark for navigation. But behind the crisp symmetry lies a chaotic and active stellar nursery, one of the most dynamic regions of star formation in the entire Milky Way. The Orion Molecular Cloud Complex, which encompasses much of what we see in Orion's sword and torso, is a colossal structure of dust, gas, and collapsing matter stretching hundreds of light-years in all directions. This massive structure includes not only the bright Orion Nebula, M42, but also Barnard's Loop, the Horsehead Nebula, M43, the Flame Nebula, the Running Man Nebula, and the obscured stellar nurseries of L1641 and L1630. Within this seething cloud of material, stars are being born in waves, sometimes alone, sometimes in clusters, sometimes in chaotic jets of plasma or expanding shells of shocked gas. It's a region full of violence and birth, of still-forming stars and fading remnants of the past. Protostars, Herbig-Haro objects, emission nebulae, reflection nebulae, and dark nebulae all coexist here, overlapping and sometimes obscuring one another. It's a place where light fights through dust, where some objects blaze while others smolder unseen. In this grand storm of creation, it's no surprise that something like V529 Orionis, a variable, mysterious, and often invisible object, might drift quietly among the chaos, largely unnoticed. Orion is also home to dying giants. Betelgeuse, for example, is a red supergiant nearing the end of its life. Its famous dimming event in 2019 to 2020 shocked astronomers and hinted at dust production, convective activity, and mass loss on a scale that mirrors, in some strange way, the questions surrounding V529. Rigel, another Orion star, is a blue supergiant, massive, young, and volatile, destined to end in a violent supernova. These are not quiet, stable stars. Orion is a constellation of extremes, and V529 may be another chapter in that dramatic story, just subtler, quieter, hiding in the wings while the giants take center stage. Further enriching Orion's layered history is the presence of stellar associations and clusters that drift in the background. The Orion OB1 association includes several subgroups of young, hot, massive stars born from the same molecular clouds. This entire region is teeming with OB-type stars, many still wrapped in their dusty birth cocoons or interacting violently with surrounding gas. These stars are short-lived but energetic, and they shape the clouds around them through intense radiation, stellar winds, and even supernovae. It's not just formation and death. Orion also hosts evidence of stellar migration. Many of the stars visible in Orion today are moving rapidly through space. Some may have originated elsewhere in the galaxy, ejected from gravitational interactions. Others are part of binary systems that have long since separated. Orion is not static, it is changing, evolving, reshaping itself with every passing millennium. And so, in this grand design, this arena of drama and formation, V529 Orionis exists like a whispered question in the middle of a roaring crowd. Unlike the blazing young stars, it does not proclaim its presence. Unlike the titanic supergiants, it does not loom with size and rage. Instead, it plays a subtler game. It appears, disappears, dims, and returns. It is not born, and it is not yet dead. It simply is, in a way that defies neat categorization. There's something symbolic about this. That amid the grandeur and spectacle of Orion's star-forging power, there lurks a star that may be shedding its layers, fading into a dusty shroud, perhaps stepping toward the planetary nebula phase, or doing something we don't yet understand at all. V529 Orionis could be the exception that proves the rule, or the outlier that hints at a rule we haven't yet discovered. It also raises the unsettling thought that Orion may hold more such secrets. If V529 has gone unnoticed for so long, what else might be slipping past our gaze in this radiant constellation? Could there be other, ghost stars, fading in and out, tucked behind the bright glow of M42 or the dusty wisps of the Horsehead? Could there be young stars just beginning to pulse and dim, or old stars collapsing behind veils of gas, never drawing attention because they do not scream? The truth is, we've mapped Orion extensively, but we may not have understood it fully. Spectacular as it is, it remains a stellar puzzle box, filled with layers, illusions, and anomalies. V529 Orionis simply reminds us that even in the most illuminated parts of the sky, darkness can hide. That beneath the canvas of the familiar lies the unknown, waiting for someone to look deeper. And perhaps that's why V529 is so fascinating. It doesn't just flicker, it contrasts. It rebels against the overwhelming light of its neighbors by fading. It stands out by disappearing. It gives us mystery. It suggests that Orion's brightest lights are only half the story. The rest lies in the subtle, in the hidden, in the stars that don't want to be seen. The story of V529 Orionis is, in many ways, incomplete. We've traced its flickering presence across the decades, catalogued its erratic appearances and disappearances, speculated on dusty veils, exotic evolutionary phases, and unseen companions, but the truth remains frustratingly out of reach. Why does it behave this way? Why does it fade so unpredictably and so completely? Why is it different from every known class of variable star? The only honest answer is, we don't know. Not yet. And that is precisely why this strange, unassuming star demands more attention, more monitoring, and more dedicated observation. Because hidden in its silence could be the next great clue to the physics of stellar evolution, or something we haven't even imagined. In astronomy, progress doesn't always come from the loudest explosions or the brightest bursts of light. Sometimes it comes from paying attention to the anomalies, the systems that don't behave, the stars that don't fit. V529 Orionis is an outlier, and outliers often hold the keys to unlocking hidden chapters of astrophysical knowledge. That's why V529 is more than just a curiosity. It's a test case, a puzzle with real stakes. And yet, despite this potential, it remains poorly monitored by modern standards. Unlike well-known variable stars that are routinely tracked by both professionals and automated surveys, V529 often goes unobserved for long periods. Its location in a crowded, bright region of the sky can lead observers to overlook it. And because it lacks a formal, widely accepted classification, and often isn't even present in some star catalogs, many monitoring programs simply exclude it. But that is precisely what needs to change. Continuous photometric monitoring of V529 Orionis could resolve many of the unanswered questions that still cloud its identity. High cadence data, recorded regularly, night after night, would allow astronomers to build detailed light curves, revealing whether the fading events follow any subtle periodicity or pattern. Even if no rhythm emerges, such monitoring could uncover smaller fluctuations between the major dimming episodes, telltale signs of pulsations, disk interactions, or hidden companions. Furthermore, coordinated multi-wavelength observations could shed light on the mechanisms behind its vanishings. Is the dimming caused by dust? Then it should glow in the infrared while fading in the optical. Is the envelope cooling or ejecting material? Then we might detect spectral lines associated with outflows, shocks, or circumstellar interactions. Are we seeing eclipses? A binary companion might reveal itself in timing deviations or spectral Doppler shifts. But none of that is possible without data, lots of it, and sustained over time. The problem is that many of the existing sky surveys are not optimized to catch something like V529. Automated surveys like Gaia or Zwicky Transient Facility, CTF, do occasionally detect variability, but they're not pointed at the same object every night. They catch flashes, spikes, and sudden changes. They work beautifully for supernovae, cataclysmic variables, and large amplitude events. But for a star like V529, whose fadeouts can be slow, subtle, and extended over months, those surveys might take a snapshot at the wrong moment, miss the key transitions, and log only fragmented data. This is where dedicated, continuous monitoring by both professionals and amateurs becomes essential. Imagine a global network of telescopes, coordinated to follow V529 every night, across seasons and hemispheres. Even modest backyard observatories equipped with CCD cameras and standard photometric filters could contribute invaluable data. If properly calibrated and standardized, this crowdsourced science could detect the next fade in real time, track it in detail, and even trigger larger telescopes to observe follow-up spectra or infrared images. This approach has precedent. Similar global campaigns have been launched for stars like Betelgeuse, KIC 8462852, Tabby star, and Acaroni borealis variables. In each case, The outpouring of collaborative monitoring helped clarify their nature, or, at the very least, refine the questions astronomers needed to ask. V529 deserves that same attention. And it's not just because of what it could reveal about itself. The bigger truth is this: we don't know how many V529-like stars are out there. If its behavior represents a rare but real phase of stellar evolution, perhaps a short-lived pre-planetary nebula stage, or a dust-obscured transition from one variable type to another, then we may be missing an entire population of such stars. And we're missing them for the same reason we almost missed V529, because they're quiet. Because they fade. Because they don't scream when something interesting is happening. But if we can crack the code of V529, we might be able to identify others. We might recognize the light curves of similar stars in archival data, reinterpret past anomalies through the lens of what we've learned, and build new models that account for these mysterious transitions. We might even revise our understanding of how common or uncommon certain stellar fates truly are. The implications could ripple through our understanding of stellar life cycles, mass loss processes, dust production, and binary evolution. V529 is like a litmus test for how well our models account for the edges and fringes of stellar behavior. If it doesn't fit, then maybe it's time we re-examine the framework. There's also a compelling philosophical case for more monitoring. V529 Orionis reminds us that we've not exhausted the sky. That even in a well-trodden constellation like Orion, there are unknowns hiding in plain sight. That the cosmos is not a static place, but a dynamic one, alive, changing, full of behavior we don't yet understand. If we don't pay attention to those changes, we risk missing the deeper truths of the universe we're trying to comprehend. And so, the case for monitoring V529 Orionis is not just about solving a mystery. It's about leaning into uncertainty. About embracing the idea that mystery still exists, and that the universe still has secrets to offer us, if only we're patient enough, curious enough, and willing enough to look. The next dimming could begin tomorrow, or next year, or in a decade. Will we be ready to catch it? Will we be watching? If we treat the fading of V529 Orionis not as a malfunction of observation but as a genuine phenomenon, something physically real, happening out there among the stars, then the question naturally follows: what exactly is causing it? What kind of process could so thoroughly and unpredictably dim a star to the point that it becomes functionally invisible to our instruments, sometimes for years? The answer is not straightforward. In fact, there may be no single answer at all. What we have instead are theories, competing, overlapping, and evolving hypotheses that attempt to explain the star's behavior using what we know about stellar physics, while acknowledging how much we still don't. The most widely accepted theory is that dust plays a central role in the dimming episodes. The idea here is relatively intuitive. If the light from V529 Orionis is being blocked, something must be getting in the way. Dust is the most plausible culprit. Not just any dust, but circumstellar dust, microscopic particles of carbon, silicates, and other elements expelled from the star itself, which then form a temporary shroud around it. If the star is shedding matter in fits and starts, that material could condense into dust clouds that orbit or drift outward. When these clouds pass between us and the star, they absorb and scatter visible light, rendering the star all but invisible in the optical range. We've seen this behavior in stars like our Corona Borealis, and to a lesser extent in young stellar objects still forming within molecular clouds. In both cases, dust plays a starring role, whether it's the product of a carbon-rich outer layer being expelled, or residual material from a protostellar disk. But V529 doesn't quite fit either mold, which is where the other theories start to unfold. One such theory suggests that V529 may be experiencing the dying spasms of its stellar envelope. If the star is entering a late stage of stellar evolution, perhaps transitioning from the asymptotic giant branch, AGB, to a preplanetary nebula phase, then its outer layers could be expanding, fragmenting, and being ejected into space. This process isn't smooth. It can happen in bursts, driven by complex pulsations, radiation pressure, and changes in the star's internal structure. As the outer shell becomes increasingly unstable, material may be shed unevenly, producing irregular, clumpy clouds of gas and dust. These ejections can drastically affect the star's brightness. Not only does the expelled material obscure the star's surface, it also alters the star's apparent temperature and color. Depending on the size, composition, and density of the cloud, the light curve could drop sharply, or gradually, before recovering over weeks, months, or even years. The chaos of this stage may account for the star's unpredictability, especially if it is not occurring in a uniform, symmetric fashion. Another possibility, though still speculative, is that V529 is undergoing stellar pulsations, but of a kind not fully understood or categorized. Pulsating stars are known throughout the Hertzsprung-Russell diagram, from Cepheids to Mira variables to RV Tauri stars. But V529 doesn't behave like any of them. Its light curve lacks the regular, sinusoidal pattern of classic pulsators. However, if it's in a transitional evolutionary phase, the pulsations may be irregular and coupled with atmospheric shock waves, driving material off the star and enabling dust to form rapidly. These so-called strange mode pulsations are predicted by some advanced models of dying, massive stars, particularly those nearing post-AGB evolution or shedding a red supergiant envelope. If V529 is in such a rare stage, it may be displaying a hybrid behavior, where intrinsic pulsations lead to episodic mass loss, and that mass loss leads to dust obscuration and brightness dips. Yet another idea enters from the opposite end of the stellar life cycle: planet-forming activity. Could V529 be a young star rather than an old one? Is it possible that the dimming events are caused by large clumps or warps in a protoplanetary disk, similar to what we've seen with stars like A Tauri or the now famous KIC 846-2852 Tabby star? If so, then the variability would stem not from dying breath, but from youthful chaos, disks, rings, and perhaps even nascent planetary bodies orbiting the star and casting shadows across its light. This model comes with its own challenges. V529 does not exhibit the strong infrared excess typically associated with young stars surrounded by thick disks, although there has been some infrared emission noted, suggesting the presence of warm dust. But without accompanying signs of stellar youth, such as high activity, X-ray emissions, or certain spectral features, it becomes harder to place V529 in this category. Still, the possibility cannot be ruled out entirely, especially if the star is in an unusual or prolonged transitional phase. Other ideas border on the exotic. Could there be a companion star or brown dwarf periodically eclipsing V529, or interacting in a way that causes the primary to shed material? Could a close-in exoplanet, perhaps one on a highly eccentric orbit, be disrupting the outer layers of the star as it passes, triggering temporary obscuration events or localized dust formation? These possibilities are difficult to confirm without high-resolution spectroscopy and radial velocity studies, but they add richness to the landscape of possibilities. In a more speculative vein, some have even considered whether non-standard processes might be at play: stellar magnetism, sudden envelope collapses, or intermittent accretion events. These are the edge cases of astrophysical modeling, where observed behavior exceeds the current boundaries of prediction. V529's erratic dimming might not just be a case of missing data. It might be a new class of behavior, one that exists in the gray area between known variable types. Each of these theories, dust shrouds, dying envelopes, unstable pulsations, circumstellar disks, carries with it a piece of the puzzle. And yet, none fully explains all observed phenomena. The fading is sometimes abrupt, sometimes slow. The recovery is not always symmetrical. The brightness doesn't always return to the same baseline. The intervals between events are irregular. The star doesn't radiate like other stars in similar categories. And yet, it's there, undeniably and confoundingly fading and reappearing. What this suggests is that the fading of V529 Orionis may not be due to any one cause. It may be multifactorial, a result of several interacting phenomena layered over one another in complex, perhaps chaotic ways. And this may be what makes it so valuable to study, because it resists simplicity. Because it forces us to refine our models. because it refuses to be an easy answer. In many ways, the fading of V529 Orionis mirrors the process of discovery itself, uncertain, nonlinear, full of doubt and wonder. Every disappearance invites new interpretation. Every reappearance brings more questions. And somewhere in that unpredictable rhythm may lie an insight we haven't yet uncovered. What if this star is telling us that stellar evolution is not a smooth path but a messy, fragmented transformation filled with detours? What if its fade-outs aren't anomalies, but missing chapters of a book we've only just begun to read? Whatever the truth may be, one thing is clear: when V529 Orionis fades, it is not simply going dark. It is speaking, in the language of vanishing light, in the vocabulary of shadows. We just need to keep listening. For a star as enigmatic and behaviorally strange as V529 Orionis, one might expect that it would be a focal point in modern astrophysics, scrutinized by survey telescopes, tracked across decades of data, and monitored in real time by both amateur and professional astronomers. And yet, somehow, V529 has slipped between the cracks. It has quietly fallen off the radar, not just in casual observation, but in the vast and powerful cataloging systems that now underpin modern astronomy. It is, quite literally, a star forgotten by many. In an era where data flows from sky surveys by the terabyte, and artificial intelligence trawls through databases to flag unusual behavior in stars, it seems inconceivable that something as dramatic as V529's vanishing act could go largely unnoticed. And yet, that's exactly what happened. Despite its location in one of the most famous constellations in the night sky, Orion, it receives almost no regular attention. The vast majority of variable star discussions, both academic and amateur, don't mention it. It's not in the crosshairs of supernova searches or exoplanet transit hunts. It's not a poster child for dusty stars or late evolutionary phases. It has been bypassed, overlooked, and quietly excluded. There are reasons, of course, none of them good, but all of them understandable. One of the biggest issues is simply its irregularity. Astronomers and surveys love predictable patterns. Cepheid variables pulse on schedule. Mirror stars rise and fall in months-long loops. Even our Corona Borealis stars, famous for their dramatic dimmings, have behaviors that can be folded into models and expectations. But V529? It doesn't pulse predictably. It doesn't fade in smooth intervals. It doesn't even conform to a rough template. It just fades, and sometimes disappears. For a star that disappears entirely, catalog invisibility becomes a real problem. The logic of automated data systems is unforgiving. If you don't show up in the latest observation, you're not there. In many sky surveys, especially those aimed at mapping dense fields or refining proper motion data, a star that vanishes without a trace will be flagged as erroneous, or at best as non-detection. Over time, this leads to exclusion from newer databases. So even though V529 appeared in earlier records and visual observations, its absence in recent CCD surveys causes modern catalogs to ignore it, or bury it beneath a sea of footnotes and flags. It gets worse. Even within the specialized variable star catalogs, where one might expect V529 to have a safe home, it has been neglected. The General Catalog of Variable Stars, GCVS, does include it, but the data is limited. Entries are sparse. There's no extensive light curve history. No modern reclassification. No intense scrutiny. It's as though V529 is acknowledged, but not truly studied. Other more comprehensive databases like AVSO's International Variable Star Index, VSX, offer minimal updates, if any. Observers scroll past, often unaware of the oddity sitting just beneath the sword of Orion. This catalog-level amnesia extends to online tools and software used by amateur astronomers. Programs like Stellarium or Sky Safari may not display V529 by default. Even in advanced settings, locating it can be difficult without precise coordinates, and when it is found, it is often devoid of the detailed metadata available for other variables. This contributes to its ghost-like presence. Many people who might want to observe V529 can't easily find it or don't know what they're looking for. It's hidden, not by distance, but by absence from the systems designed to reveal. There is a psychological component here too. In astronomy, the narrative tends to gravitate toward the spectacular. Supernovae, black holes, galaxies colliding. When a star's primary feature is that it occasionally stops being visible, it doesn't spark headlines. It doesn't crash Twitter. It doesn't get featured in glossy magazines or TED Talks. It's an absence story. A whisper in a discipline that often chases roars. And yet that whisper might carry a message we've missed. Because fading stars don't just disappear, they transform. They obscure themselves. They defy categorization. And V529 is not alone in this behavior. There may be others, stars that have similarly fallen through the gaps, lost to the logic of cataloging systems that prioritize brightness, consistency, and confirmable coordinates. If V529 has been forgotten, then surely others have too. The question isn't just what happened to this one star, but what else have we missed? In this way, the forgetfulness surrounding V529 becomes more than just an administrative issue. It reflects something deeper, a vulnerability in our tools, our models, and even our curiosity. In the rush to map the cosmos, we sometimes overlook the parts that don't fit neatly into our frameworks. We leave behind the quiet stars, the complex stars, the stars that resist being simplified. And in doing so, we may miss exactly the kinds of objects that challenge our understanding most. It's also a kind of astronomical tragedy. Not in the sense of catastrophe, but in the quiet loss of attention and meaning. V529 was seen. It was tracked. It was wondered about. And then, over time, it simply stopped being part of the conversation. Fading from visibility, yes, but also fading from the collective awareness of the astronomical community. Not through malice. Not through failure. But through the natural gravity of large systems that prioritize what's easiest to see. And yet, it's still there. Still flickering. Still fading. Still returning. Still resisting the urge to be forgotten entirely. Like a ghost star lurking in the heart of Orion, it reminds us that not everything important shines brightly. That some truths must be pursued through shadows. That some mysteries demand attention not in the moment of spectacle, but in the long, slow patience of watching something that doesn't behave the way we expect. A V529 Orionis, nestled quietly within the most famous constellation in the sky, can elude our attention for decades, appearing, disappearing, resisting classification. Then the question practically asks itself, how many more are there? How many other stars are out there, slipping between the pixels of our sky surveys, hiding behind dust, flickering in the peripheries of light curves, waiting to be noticed? Could V529 be merely one example of a broader, more elusive population, an entire class of stars that don't just defy expectations but evade detection altogether? This isn't just poetic speculation, it's grounded in real limitations of the way we currently observe and catalog the universe. Our best telescopes and surveys, from Gaia to TESS to CTF, have revolutionized our understanding of stellar behavior, catching supernovae in their earliest moments, flagging exoplanet transits from light years away, and mapping the precise motions of billions of stars. But even with all this power, we are still missing things. Our instruments, brilliant though they are built on thresholds, brightness limits, cadence intervals, detection algorithms tuned to find certain types of variability. Anything that falls outside these parameters risks being ignored, misclassified, or lost. Imagine a star like V529 Orionis that fades gradually, drops below a survey's detection limit, and then reappears years later. If that dimming coincides with the gaps between observations, it could appear in one data set, vanish in the next, and never be cross-matched again. Now imagine a fainter version of V529, perhaps located in a less iconic constellation, one that isn't bathed in attention like Orion. Its entire life could pass unnoticed, not because it isn't doing anything interesting, but because it's doing something too subtly. In fact, the sky is full of such objects. In recent years, astronomers have found a small handful of vanishing stars, objects that were present in older catalogs or photographic plates, yet cannot be located in modern surveys. Some of these may be errors. Others may be genuine supernovae or catastrophic collapses. But a few, just a few, seem to behave like V529. They vanish, then return, without any explosive event to explain the change. They don't fit the narrative of violent death or stellar formation. They just change. Gradually. Quietly. It's worth considering the biases in how we study variable stars. Much of our attention has gone to stars that pulse predictably, Cepheids, are our Lyrae, stars that erupt spectacularly, novae, supernovae, or stars that host planetary transits. But what about the stars that don't fit any of these molds? The ones that flicker out of phase, that fade with no warning and for no obvious reason? Our entire classification system is built around light curves, patterns of brightening and dimming that can be measured, repeated, and categorized. When a star like V529 refuses to follow any pattern, it becomes harder to model, harder to search for, and, tragically, easier to ignore. This suggests a broader blind spot in our understanding of the sky. Not just a missing piece in the map, but a kind of systemic invisibility, a situation where our tools, methods, and assumptions all conspire to miss an entire class of stellar behavior. We look for the stars that blink on schedule, that flare on cue. But stars don't owe us consistency. They evolve. They die. They hide. And perhaps some of them never shine the same way twice. It's possible that V529 Orionis is part of a continuum, a bridge between known variable types and something stranger, something rarer. Maybe it's not alone. Maybe there are dozens, hundreds, or thousands of similar stars scattered across the sky, waiting for someone to look a little longer, dig a little deeper, or re-examine an old plate from a forgotten observatory drawer. Some may be buried in archival data, faint detections that were never followed up, anomalies flagged as noise, stars recorded once and then silently excluded from future catalogs because they failed to meet a brightness threshold. Others might be hiding behind veils of dust in star-forming regions, their light warped or blocked entirely. Still more might reside in crowded fields, lost in the glare of brighter neighbors, or in parts of the sky we've simply scanned too infrequently. There's also the tantalizing idea that some of these, ghost stars, could be objects undergoing extreme and unusual transformations, late thermal pulses, envelope collapses, or transitions into white dwarfs obscured by their own ejected matter. These aren't just random flickers, they're moments of transformation. By the time we notice, the star may have changed form entirely, becoming a different kind of object, no longer recognizable as what it once was. If so, then the true rarity isn't in the behavior, but in catching it in the act. This is where V529 Orionis becomes a kind of cosmic canary in the coal mine. Its flickering light, its disappearances, its refusal to play by the rules, these might all be signals of a phenomenon that is more widespread than we know, but simply too subtle to detect en masse. Like gravitational waves were before LIGO. Like exoplanets were before Kepler. Hidden, but not non-existent. And that makes the case for renewed scrutiny all the more compelling. If we want to find more V529-like stars, we need to rethink how we approach sky surveys. We need new algorithms, tuned not just for sharp peaks and dips, but for absence, for silence, for inconsistency. We need to revisit old data with new eyes. To search again through catalogs, especially those with partial or uncertain entries. We need to create alert systems not just for brightening events, but for vanishing acts, for stars that were there and are suddenly not. The discovery of a single star that behaves this strangely would be interesting. But the possibility that there are more, that an entire family of stars is hiding across the sky, would be revolutionary. It would mean we've misunderstood a part of stellar evolution. It would mean we've been looking at the universe with incomplete vision. It would mean the map we thought was finished has blank spaces still waiting to be filled. And V529? It would become the Rosetta Stone for a hidden dialect of stellar behavior, a translator between what we know and what we have yet to comprehend. Because if stars can hide in Orion, they can hide anywhere. What makes V529 Orionis so compelling isn't just that it fades. Many stars do. It's not even that it fades to invisibility, some do that too. What sets V529 apart is the combination of unpredictability, location, and mystery, all wrapped in an enigma that refuses to be categorized. It is a star that dares to defy everything we thought we understood, not from some obscure corner of the galaxy, but from the beating heart of one of the most recognizable constellations in the night sky. It's the contradiction that makes it fascinating. A celestial ghost, flickering right under our nose, in a place we thought we had fully explored. At the heart of its allure is the unpredictability. V529 doesn't play by any rhythm we've come to expect. It doesn't follow the gentle regular pulsations of Cepheid variables, or the explosive tempers of novae. It comes and goes, fades and returns, with no clear cycle, no neat curve, no textbook pattern. Some fades are abrupt, some are slow. Some recoveries take months, others happen almost imperceptibly. There's no warning, no countdown, and often no consistency. It is a mystery in motion, and every new observation rewrites the previous assumptions. The lack of predictability isn't just a nuisance for astronomers, it's a feature of the mystery. Every time the star disappears, we're left wondering, is this the last time we'll see it? Will it return in a month? A year? Ever? And when it does come back, it's not always the same. The brightness baseline changes. The color may shift. Something different returns to us each time, as though the star is not just flickering, but evolving in real time, transforming before our eyes. Then there's the invisibility. Not just the figurative kind, where a star is too faint for amateur observers or tucked into a crowded field. V529 Orionis becomes truly invisible. Even with quality optics and clear skies, it vanishes. Gone from charts. Gone from catalogs. Gone from memory. It's a reminder that stars, which we often think of as eternal and fixed, are in fact dynamic and vulnerable to their own processes. That something so massive, so luminous, could disappear so easily shakes our sense of permanence when looking up at the sky. This disappearing act forces us to confront an uncomfortable truth. Our understanding of the cosmos is far from complete. We catalog stars, measure their spectra, estimate their ages, and model their fates. But here is V529 uncooperative, slipping through the fingers of our scientific grip. Not because it defies physics, but because it highlights the limitations of our observation, the assumptions baked into our models, and the overconfidence we sometimes have in thinking we've mapped the sky thoroughly. What makes this even more striking is its location. Orion isn't some forgotten region. It's the cosmic centerpiece of winter nights in the northern hemisphere. Children learn to recognize its belt. Telescopes point to its nebulae. Its supergiants are studied endlessly. And yet, in this famed neighborhood, V529 lurks, a resident with strange habits that most neighbors have ignored. It's as if someone whispered a secret in the middle of a loud concert, and no one noticed. This juxtaposition between visibility and mystery, between a well-lit stage and a performer who keeps slipping behind the curtain, is what makes V529 Orionis so alluring. It dares us to re-examine what we thought was familiar. It reminds us that even in the most mapped, studied, and admired regions of the cosmos, there are still surprises. Still outliers. Still secrets that whisper rather than shout. There's a poetic tension in that. Stars, after all, are often metaphors for constancy. They shine through time, through myth, through history. And yet here is a star that refuses that role. A star that plays hide-and-seek with our expectations. A star that says, "You don't know me." Not really. This rejection of our frameworks is not a dead end, it's an invitation. V529 beckons to curious minds. It asks for patience. It asks for obsession. It asks for humility. For in its fading, we are reminded that some truths aren't revealed in brightness but in absence. Some mysteries are not in what we can see, but in what disappears just as we begin to understand. And that's what elevates V529 from an astronomical curiosity to something more profound. It becomes a symbol of the unknown still lurking in our observations. A quiet protest against the idea that we've figured everything out. A challenge wrapped in shadows. It's not a loud mystery. It's not explosive. It's not cinematic. It's slow. It's patient. It waits. And maybe that's the most intriguing thing of all, because in the age of instant discovery, V529 Orionis plays a longer game. V529 Orionis is a cosmic reminder that the universe is not a solved puzzle, it's a living riddle. A flickering dot among thousands, yes, but also a bold gesture of resistance against the idea that everything above us is now known. It's easy to fall into that trap. With our vast sky surveys, space telescopes, and data pipelines capable of processing billions of stars, one might assume the sky holds no more surprises. And yet, here it is, a star that fades sometimes into nothingness, only to reappear on its own timetable, governed by laws we haven't yet pinned down. V529 plays a kind of celestial hide and seek, not out of malice or mischief, but simply as a consequence of what it is. And perhaps the most humbling part of this entire journey is not what the star is doing, but where it's doing it. Not on the fringes of some uncharted galactic cluster, not buried behind a cloud in an obscure corner of the sky, but in Orion. The hunter. The showcase. The cosmic centerpiece of every clear winter night. There, in the folds of its sword, a star has been flickering in and out of existence, and we almost didn't notice. It's almost poetic, the way the universe humbles us. With all our tools and catalogs, with algorithms trained to spot anomalies and AI models scanning petabytes of sky maps, something still slips past. Something that shouldn't. That can't. But it does. And when we do notice it, when someone decides to point their lens or their telescope back at that forgotten dot, we're left with a feeling that's equal parts awe and embarrassment. How could we miss this? And what else have we missed? Because if the universe can hide a star in Orion, right in front of us, then what else is it hiding? How many phenomena do we overlook not because they're too far, or too faint, but because they don't behave the way we expect them to? Because they're inconvenient. Because they don't light up in the way we've been trained to see. V529 is a bright flare of anti-pattern, a soft rebellion in the sky that says, "You've only scratched the surface." In that way, it's more than just a variable star. It's a metaphor for science itself. For all its rigor, observation, and modeling, science is still an act of listening to the unknown. It requires openness to contradiction. It asks for the humility to accept when our frameworks don't fit. And V529 offers just that, a contradiction we haven't resolved, a whisper we haven't decoded. It challenges us to consider that discovery doesn't always come from deeper technology, but from deeper attention. From asking questions not just about what is seen, but about what vanishes. From returning to the familiar sky and daring to look again, not for the brightest, or the loudest, but for the quiet one that keeps disappearing. The universe does not reveal itself all at once. It unveils in layers, in slow fades and sudden reappearances, in misclassified entries and neglected footnotes. It hides things in plain sight, not because it is trying to trick us, but because we are still learning where to look. V529 Orionis is not a trickster star. It is not deliberately evasive. It is simply complex, patient, different. And yet it plays its role perfectly in this vast game of celestial hide and seek. Sometimes there. Sometimes not. Sometimes bold enough to be caught in the corner of a telescope's gaze, and sometimes gone so thoroughly it seems like it was never real. But it is. It's real. It's there. And it's waiting. Waiting for the next person to notice. Waiting for someone to finally connect the dots between its behavior and the grander mechanisms of stellar evolution. Waiting, maybe, for us to understand something not just about the universe, but about our place in it, still surrounded by mysteries, still standing on the edge of the unknown, still very much in the middle of the game. And so, beneath the cold and ancient stars, we arrive at the final note, a quiet tribute to the vanishing star of Orion. V529 Orionis, neither the brightest nor the boldest, but perhaps one of the most haunting. A ghostly flicker cradled in the folds of the hunter's sword, it pulses not with certainty, but with mystery. It is the kind of star that doesn't shout for attention. It doesn't explode in glory or dazzle with color. Instead, it leaves and returns. And each time it does, we are reminded of how little we truly grasp about the sky we think we know so well. Orion, the mighty hunter, dominates the night. Its belt is iconic, its sword unmistakable, its great nebula a birthplace of stars. We teach children to find it. We name ships after it. We dream under it. And yet, within this constellation's gleaming architecture, one star refuses to conform. It fades not with age, but with intention. Not permanently, but on its own secret clock. V529 Orionis is Orion's heartbeat in shadow, its quiet contradiction. Perhaps it is this contrast that makes its presence so profoundly poetic. That amid giants like Betelgeuse and Rigel, amid the brilliant birthing grounds of M42, V529 dares to flicker in and out of being. Its existence feels like a secret, a whispered clue that the universe still guards its deepest mechanisms closely. That there are still places where the map fades, where definitions blur, where even light can be silenced. When we look up at Orion, most eyes will trace the bright stars, the proud geometry of the celestial hunter. But for a few, those who search for strangeness, who listen for silences between pulses, there's V529. Hard to find. Easy to miss. But impossible to forget once known. It represents the kind of wonder that grows over time, not from spectacle, but from the slow realization that the cosmos is filled with lives and deaths, signals and silences, that operate beyond our gaze. It's not the grand finale of a supernova or the clockwork regularity of a pulsar. It's something softer, quieter. A disappearing act with no applause. A light that dims not to end, but to be noticed. And so we end not with a revelation, but with a question left open. A star still not fully explained. A mystery that refuses to close its book. In a sky so full of answers, V529 Orionis remains a riddle. A vanishing trace of light that returns just long enough to say, "I'm still here." But not always. Tonight, when Orion rises in the east, and you follow the line of its belt down toward the sword, let your gaze linger a moment longer. Look just to the side of brilliance. Past the obvious. Into the space where a star once was, and might be again. Maybe you'll see it. Maybe you won't. But you'll know it's there. Flickering. Waiting. Hiding in plain sight. V529 Orionis, the vanishing star of Orion. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.